Warp drive sounds like the answer to everything. Fold space, skip the distance and reach the stars. Problem solved. Except the universe does not care about our solutions. And the gap between stars has a few tricks up its sleeve that no engine, not even one that bends the fabric of space-time, can simply outrun. If this is the kind of conversation you wish more people were having, make sure to give this video a like. Now let's get started. Let us talk about the scale problem, because this is where the conversation needs to start, even if it is where most conversations about warp drive never bother to go. When people imagine interstellar travel, they usually picture something like this: a sleek ship sitting in orbit, a destination glowing in the distance, a dramatic jump through a visual warp effect. The whole thing feels manageable in the imagination because our brains are simply not built to genuinely process cosmic distances. We evolved on a single planet, navigating distances of tens or hundreds of kilometers at most. The cosmos does not care about what our intuition can handle. So let us try a different approach. Let us try to actually feel the scale, rather than just saying the numbers and nodding along. The Milky Way galaxy is roughly 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars, depending on which estimate you are working from, because even counting them is not straightforward. 100,000 light-years. A single light-year is approximately 9.46 trillion kilometers, so 100,000 light-years is 9.46 times 10 to the 17th power kilometers. A number so large it is essentially meaningless to the human mind as a raw figure. So let us shrink it down. Let us use a scale model, take our entire solar system, from the Sun all the way out to Neptune, which orbits at roughly 4.5 billion kilometers from the Sun. In our scale model, let us compress the whole thing, the entire solar system, down to the size of a single grain of sand. 1 grain of sand. That is our solar system. In that model, the nearest star system to us, which we will not name specifically right now, but which most people have heard of, would be sitting roughly 3 meters away from our grain of sand. 3 meters. That actually sounds almost cozy, does it not? You could walk it in 2 steps. But here is where the model breaks your brain. That 3-meter gap, in real terms, is approximately 40 trillion kilometers of vacuum. Some estimates put it closer to 41 or 42 trillion kilometers, depending on the precise reference point used. 40 trillion kilometers of essentially nothing. No planets, no warmth, no atmosphere, no sound. Just the interstellar medium, which, and this is crucial, is one of the most extreme voids in the known universe. The interstellar medium, that is the technical term for the material between star systems. And when you hear the word material, do not picture anything you would recognize as matter from your daily life. The density of the interstellar medium averages roughly 1 atom per cubic centimeter in the regions between stars. 1 single atom per cubic centimeter. For comparison, the air surrounding you right now contains approximately 2.7 times 10 to the 19th power molecules per cubic centimeter. That is 27 quintillion molecules. The most advanced vacuum chambers ever built by human engineers, the ones used in particle physics experiments and gravitational wave detectors like LIGO, still contain roughly billions of particles per cubic centimeter. Even our best artificial vacuums are crowded compared to the space between stars. The interstellar void is not just empty in the way a room feels empty. It is empty in a way that has no real equivalent in human experience. It is a kind of emptiness that is almost philosophical in its totality, and it stretches for 40 trillion kilometers in every direction between each and every stellar system in the galaxy. Now multiply that gap by the 100 billion stars in the Milky Way. Think about what it means to cross from one side of the galaxy to the other. Think about what it means to leave the Milky Way entirely and attempt to reach Andromeda, our nearest galactic neighbor, sitting 2.5 million light-years away. Not 40 trillion kilometers, 2.5 million light-years. In our scale model with the grain of sand solar system, Andromeda would be roughly 75 kilometers away, 75 kilometers. In a model where our entire solar system is a grain of sand, that is the stage we are operating on. That is the universe we are proposing to navigate now. Here is where the warp drive conversation genuinely gets interesting and genuinely gets dark, because the naive hope is this: if we just go fast enough, the distance does not matter. And there is a version of that logic that holds in relativity. The faster you travel, the more time dilates, the shorter your subjective journey feels. At very high fractions of the speed of light, you could theoretically cross enormous distances in what feels like a short time to the travelers aboard the ship. This is real physics. It is called time dilation, and it is one of the confirmed, experimentally verified consequences of special relativity. But here is the problem. Time dilation only helps the people on the ship. Back home on Earth, in whatever civilization sent you, centuries or millennia are passing. You arrive at a distant star system and you step off the ship, perhaps only a few years older by your own biological clock. But the civilization that launched you is gone. The language has changed. The people you loved are dead. Their grandchildren's grandchildren's grandchildren are dead. Everything you knew is history. That is not a speed problem. That is a distance problem that no amount of speed fully solves, because speed trades your subjective time against everyone else's objective time. You are not beating distance. You are trading it for a different kind of loss. And that is before we even get into what warp drive specifically proposes to do, which is something entirely different from just going fast. Warp drive, in the Alcubierre framework, does not accelerate a ship through space. It bends space itself. It compresses space in front of the vessel and expands space behind it, creating a bubble of flat space-time in which the ship sits essentially stationary, while the geometry of the universe shifts around it. In theory, this sidesteps the time dilation problem entirely. The ship is not moving through space. Space is moving around it. The travelers do not experience relativistic effects the way they would at near-light velocities. They could, in principle, travel vast distances and arrive with the same amount of time, having passed for both them and people back home. On paper, this is remarkable. It is elegant. It is the kind of physics that makes you feel like the universe might be navigable after all. And then you start looking at the requirements, and everything changes. The Alcubierre metric, that is the formal name for the mathematical description of the warp bubble, requires something that does not cleanly exist anywhere in nature as we currently understand it. It requires something called exotic matter. Specifically, it requires matter with negative energy density. Not just low energy, negative energy, matter that has less than zero energy. This is not the same as antimatter, which has positive energy and positive mass. Exotic matter with negative energy density is a different beast entirely. It is the kind of thing that, if it exists in usable quantities, would behave in ways that violate every intuition you have about how physical objects work. A ball of negative energy density matter under gravity would fall upward. Its gravitational effect on other objects would be repulsive rather than attractive. It would, in some formulations, have a negative inertial mass, meaning that if you pushed it to the right, it would accelerate to the left. Does this stuff exist? There is a hint that something like it might exist in a very limited and very quantum mechanical context. The Casimir effect, named after the Dutch physicist Hendrik Casimir, who predicted it in 1948 and which was experimentally confirmed decades later, demonstrates that two uncharged metal plates placed extremely close together in a vacuum experience a tiny attractive force. This force arises because the quantum vacuum The seething, fluctuating ground state of space itself has slightly less energy between the plates than outside them. In a very technical sense, the region between the plates has a negative energy density relative to the surrounding vacuum, but the Casimir effect operates at nanometer scales. The energy differences involved are extraordinarily tiny. The gap between what the Casimir effect demonstrates and what an Alcubierre warp bubble would require is, by some estimates, not just large, but almost incomprehensibly large. Harold White at NASA's Johnson Space Center spent years working on ways to reduce the exotic matter requirements of the Alcubierre metric and made genuine progress on the theoretical side, showing that certain modifications to the shape and thickness of the warp bubble could dramatically reduce the exotic matter needed. That work was real and it was meaningful. But even after those optimizations, the amounts of exotic matter required are still far beyond anything we know how to produce or collect or store, and the energy requirements, even setting aside exotic matter, are in a class of their own. Here is a number that should genuinely stop you. Early calculations on the Alcubierre drive suggested it would require an amount of energy equivalent to the total mass energy of the planet Jupiter, the largest planet in our solar system, more than 1,300 times the volume of Earth, converted entirely to energy just to power a single warp bubble for a single journey. Later, more refined analyses brought that number down. There are papers suggesting that with the right geometric configurations, the energy requirements could be reduced by many orders of magnitude. White's work at NASA was partly focused on this, and it is possible, genuinely possible, that future theoretical refinements will bring it down further. But even the optimistic estimates place the energy requirements far beyond anything humans have ever contemplated engineering. We are not talking about a more efficient rocket engine. We are not talking about a fusion reactor a few generations more advanced than what we have now. We are talking about energy scales that dwarf the output of entire civilizations, let alone single nations or space programs. The Sun outputs approximately 3.8 times 10 to the 26th power watts of energy every second. That is the entire power output of our star. Some of the calculations around warp drive energy requirements approach or exceed that figure for a single journey. We are not close to harnessing the total energy output of our own Sun, not even remotely. Our entire global civilization currently runs on roughly 2 times 10 to the 13th power watts. The Sun outputs roughly 10 trillion times more energy than every power plant, engine, and solar panel on Earth combined, and we would need something approaching that for warp drive for a single trip. That is not an engineering problem you solve in a century. That might not be a problem you solve at all with matter and energy as we currently understand them. We started with the scale, the 40 trillion kilometers of void between stellar systems, the 100,000 light-year width of a galaxy we have barely started to explore, the 2.5 million light-years to our nearest galactic neighbor. And then we introduced the one thing that seemed like it might cheat all of that: warp drive, real physics, published equations, peer-reviewed science. And already, before we have even gotten to the strangest and most unsettling problems with warp drive, we are looking at exotic matter requirements that border on the philosophically absurd and energy scales that dwarf the output of our entire star. But here is what I need you to hold on to: the exotic matter and the energy. Those are arguably the most solvable problems on the list. What comes next? The things we have not talked about yet. Those are the ones that should genuinely give you pause. There is a radiation problem with warp drive that some physicists believe would make the ship itself into something like a weapon of mass destruction the moment it drops out of warp. There is a navigation problem so fundamental it calls into question whether you could ever steer a warp bubble once it was active. And there is a deeper cosmological reality, something baked into the structure of the universe itself that puts a kind of ceiling on the very concept of reaching the stars, regardless of how fast you travel. Let us pick up exactly where we left off, because we established the scale, we established the energy problem, we established the exotic matter problem, and I told you those were arguably the most solvable issues on the list. Now we get to the ones that are harder, much harder. Let us start with the radiation problem, because this one is not speculative. This one comes directly from the mathematics of the Alcubierre metric itself. And when physicists first started working through the implications seriously, what they found was deeply uncomfortable. Here is what happens inside a warp bubble physically according to the equations as the bubble moves through space. Remember, the bubble is not moving through space. Space is moving around it. But from the perspective of an outside observer, it has an effective velocity. It sweeps up particles. The interstellar medium we talked about a bit ago, that near-perfect vacuum with roughly 1 atom per cubic centimeter, is not truly empty. There are particles in there, hydrogen atoms, helium nuclei, dust grains, cosmic ray particles, photons of various wavelengths streaming in from every direction. A warp bubble, as it travels, would collect these particles in front of it. They would pile up at the leading edge of the bubble wall like snow building up on the front of a plough. And here is the critical part. Because of the geometry of the bubble, the way space-time is curved around it, those particles would not just sit there harmlessly, they would be blue-shifted, dramatically blue-shifted. They would gain enormous amounts of energy relative to the interior of the bubble. Blue shifting is what happens to radiation and particles when they are compressed toward an observer, the same physical process that makes the siren of an ambulance sound higher pitched as it approaches you, but applied to electromagnetic radiation and particle energy. As particles pile up at the leading edge of a warp bubble, traveling at effective superluminal velocities, the energy of those particles, from the perspective of anything inside the bubble, would be amplified to extraordinary levels. A 2012 paper by physicists Stefano Finazzi, Stefano Liberati, and Carlos Barceló, published in a peer-reviewed physics journal, worked through the quantum field theory of the warp bubble in detail. What they found was that the interior of the bubble would be flooded with high-energy radiation, not a little radiation, lethal levels, potentially planet-destroying levels, depending on the journey length and speed. But it gets worse, because here is the really unsettling part. The paper found that the radiation would also build up in ways that the people inside the bubble could not control, could not monitor, and could not release. The geometry of the warp bubble, by its very design, isolates the interior from the exterior in a causally disconnected way. What this means in plain language is that a person inside a warp bubble cannot send any signal, not a laser, not a radio wave, not anything that propagates at the speed of light, to the outer wall of the bubble, because the outer wall is, in the frame of the bubble's interior, moving away faster than light can reach it. And if you cannot send a signal to the wall of the bubble, you cannot steer, you cannot turn, you cannot slow down, you cannot drop out of warp early. Once the bubble is active, you are, in the most literal physical sense, along for the ride with no ability to influence the journey from inside. This is not an engineering problem waiting for a clever solution. It is a geometric consequence of the physics. The causal structure of the Alcubierre space-time means that the interior is fundamentally isolated from the engine, so to speak. The bubble has to be created and controlled entirely from outside, which means that, under this framework, you cannot create your own warp bubble from inside a ship that is sitting in flat space-time. You would need someone or something outside to build the bubble around you, and once you are inside it, you would need external infrastructure to modify or stop it. This has enormous practical implications. It suggests that warp travel, if it were ever achievable, might require a network of fixed warp generators, infrastructure already in place at the destination and along the route, rather than a self-contained ship that launches from a planet and goes where it wants, which transforms the whole concept from a starship into something more like a train system. A train system that requires construction in interstellar space before a single journey can take place. But here is where the conversation pivots in a direction that most people have never considered. Because there is another problem with the warp bubble that goes beyond engineering and into something almost poetic in its cruelty. The radiation that builds up on the leading edge of the bubble, the particles and photons swept up during the journey, does not just endanger the crew. It gets released at the destination. Think about what that means. You travel across several light years using a warp bubble. Along the way, you have been sweeping up every particle and photon in your path, compressing them, blue shifting them, building up an enormous reservoir of high-energy radiation on the front face of your bubble. And then you arrive, you drop out of warp, the bubble collapses, and all of that accumulated, compressed, enormously energetic radiation is released simultaneously in the direction of travel. The destination, the star system you just arrived at, gets hit with what some analyses describe as a burst of radiation comparable to a gamma-ray event, a focused high-energy discharge in the direction of arrival. If that destination has planets, those planets are irradiated. If it has a biosphere, that biosphere is in serious trouble. If there is anyone there, any civilization, any life, they have just been on the receiving end of what is functionally a weapon. This is not a minor side effect to engineer around. It is a consequence of the physics itself. And it raises a question that is almost philosophically paralyzing once you really sit with it. If warp travel releases destructive radiation at the destination, then any civilization advanced enough to build warp drives faces an existential ethical constraint on using them. Every time you arrive somewhere, you potentially sterilize it. Every time someone arrives at your home system, you potentially get sterilized. Some researchers have suggested this could be part of the answer to the Fermi paradox, that famous question of why. In a universe full of stars and presumably full of other intelligent life, we see no evidence of anyone out there. If warp travel is physically self-defeating in the way these calculations suggest, then maybe the universe does not look like a busy highway of interstellar civilizations, because the physics makes such highways catastrophic. That is speculative. I want to be clear about that. The connection between warp drive radiation effects and the Fermi paradox is not a mainstream scientific consensus. It is a thought experiment, a possibility that falls naturally out of the physics when you let yourself follow the logic. But it is a thought experiment that some serious people take seriously, and it is worth holding in mind as we go deeper. Now let us step back from the specific problems of warp drive for a moment and look at the universe from a wider angle, because there is a cosmological reality that does not get talked about nearly enough in conversations about interstellar travel, and it is one that applies regardless of your propulsion method. Warp drive, generation ships, laser sail probes, anything, the universe is expanding. You probably already know that. It is one of those facts that gets mentioned so often in popular science that it starts to feel like background noise. But I want you to actually think about what it means for interstellar travel, because the implications are stranger and more profound than the headline usually suggests. The universe is not just expanding, it is expanding at an accelerating rate. Edwin Hubble's observations in the 1920s established that distant galaxies are receding from us, and the farther away they are, the faster they are receding. That is cosmic expansion, driven by what we now call dark energy, a component of the universe that makes up approximately 68% of its total energy content, whose exact nature we still do not understand. In 1998, two independent research teams, one led by Saul Perlmutter and one led by Brian Schmidt and Adam Riess, discovered, using observations of Type Ia supernovae as standard candles across cosmic distances, that the expansion of the universe is not slowing down. It is speeding up. That discovery earned Perlmutter Schmidt and Riess the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of the universe's future. What does accelerating expansion mean for interstellar travel? Within the Milky Way, the effects of cosmic expansion are negligible. Gravity binds our galaxy together strongly enough that individual stars are not being pushed apart by dark energy at any meaningful rate. The same is true of the local group, the small cluster of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller satellite galaxies. But beyond the local group, beyond the gravitationally bound structures in our immediate cosmic neighborhood, expansion wins. And it wins increasingly over time. Right now, there is a distance, called the Hubble radius, sitting at roughly 14 billion light-years from us, beyond which the recession velocity of space itself exceeds the speed of light. Objects beyond that boundary are receding from us faster than light can travel. They are not moving through space faster than light. That would violate relativity. Space itself between us and them is expanding fast enough that light emitted toward us from there will never reach us. We cannot see them, we cannot signal them, and we cannot reach them no matter how fast we travel. And because expansion is accelerating, that boundary is not static. It is closing in, very slowly, on human timescales, but on cosmological timescales, the observable universe is shrinking. There are galaxies we can currently see that are slowly, over billions of years, crossing into permanent unreachability. The light from them will eventually redshift to zero detectable energy. They will fade from our sky, not because they stopped existing, but because the universe between us and them stretched beyond any possible connection. This is where the conversation about warp drive hits a kind of ceiling that has nothing to do with engineering. Even with a perfect warp drive, no exotic matter problems, no radiation issues, no navigation constraints. There are regions of this universe that are already permanently beyond our reach, not because of speed, because of geometry, because of the structure of space-time on the largest scales. A paper by Krauss and Scherer, Lawrence Krauss, who you may know as the author of A Universe from Nothing, and Robert Scherer, published in 2007 and titled The Return of a Static Universe and the End of Cosmology, argued that in the far future, as dark energy continues to accelerate expansion, the universe will eventually look to any civilization that exists at that time as if it contains only their own galaxy. Everything else will have receded beyond the observable horizon. There will be no evidence from within that future Milky Way that a larger universe ever existed. The cosmic microwave background, the afterglow of the Big Bang that we use today as one of our primary tools for understanding cosmological history, will have redshifted to wavelengths too long to detect. Future civilizations, if they exist, may have no way of knowing that the universe is as vast as we know it to be today. They will inherit a cosmological darkness we have not yet experienced. Now, we are speaking here of timescales of tens of billions of years. This is not a problem for any civilization planning interstellar travel in the next few centuries, but it illustrates something important. The universe has not just built distance into its architecture, it has built an expanding, accelerating distance. A distance that grows, a distance that, in the fullness of cosmic time, swallows entire observable horizons. The loneliness between stars is not just vast, it is increasing. Here is something I want you to carry with you. We have now talked about what warp drive actually requires. what it actually does, and what the universe's own expansion means for the concept of reaching the stars. And we have not yet talked about the deepest layer of the problem, which is not about any specific technology at all. It is about what the distances mean, not just physically, but for any civilization that tries to spread across them, for communication, for identity, for the very concept of a shared civilization, because here is a question that should be haunting you right now. Even if you could cross 40 trillion kilometers to the nearest star system, even if you arrived safely, without the radiation burst sterilizing anything at the destination, how long would it take for a message to come back? How do you maintain any kind of coherent relationship with Earth when the speed of light means your fastest possible signal takes years to arrive? How do you stay human in any meaningful sense across that kind of separation? That question is where we will venture into now, and I promise you, the answer is stranger and more uncomfortable than you are expecting. Let us start with a thought experiment, a simple one, but one that I think will unsettle you in a way that pure physics cannot. Imagine humanity has solved it, all of it. The exotic matter, the energy requirements, the radiation problem, the navigation constraints. Imagine a working warp drive exists, sitting in a shipyard somewhere in orbit above Earth, ready to go. A crew of 20 people boards it, they wave goodbye, they activate the drive, and they travel to a star system roughly 12 light-years away, one of several known to host potentially interesting conditions. The journey, thanks to the warp bubble, takes them 6 months of subjective time. They arrive, they explore, they find something extraordinary, and then they send a message home. That message travels at the speed of light. Because no matter how advanced your propulsion technology becomes, information, signals, radio waves, laser pulses, anything we currently understand as communication propagates at the speed of light through flat space-time. There is no warp drive for a radio signal. There is no shortcut for a photon carrying news 12 light-years away. The message takes 12 years to arrive. By the time Earth receives their transmission, those 20 explorers have already been gone for 12.5 years. The scientists who designed the mission are 12 years older. Some of them may have died. The political landscape that funded the expedition has shifted. There have probably been 2 or 3 major elections, several economic upheavals, possibly a war or 2. The cultural moment that made the mission feel important has passed and been replaced by something else entirely. And the explorers, waiting for a response to their message, they have to wait another 12 years for any reply to reach them. 24 years round trip for a single exchange of information, a conversation that, on Earth, might take 30 seconds. We found something, what should we do? Here is what we think you should do. Takes nearly a quarter of a century, across 12 light-years. Now push it further. Imagine the crew travels not 12 light-years, but 100, or 1,000, or to the far side of the Milky Way. The communication delay scales with the distance. A civilization spread across even a modest portion of the galaxy, say a few hundred light-years, would have regions so isolated from each other that centuries pass between messages, not years, centuries. What does a civilization even mean under those conditions? What does belonging to a shared culture mean when the culture you left has had 300 years to evolve by the time your next message arrives? What does governance mean? Law? Identity? The concept of a unified human species? This is not a new question in science and philosophy. Scholars who study what is sometimes called the sociology of interstellar civilizations, a field that sits at the intersection of physics, anthropology, and futurism, have thought about this deeply, and the conclusions they tend to arrive at are humbling. Any civilization that spreads across interstellar distances will almost certainly fragment. Not through conflict necessarily, though conflict is plausible enough, but through simple divergence, through the inexorable pressure of isolation and independent experience. Two populations separated by hundreds of light years, unable to communicate in anything resembling real time, experiencing different environments, different challenges, different discoveries, will evolve culturally, linguistically, perhaps biologically, in different directions. Given enough time, they may become as alien to each other as different species. There is a term used sometimes in this context, borrowed from biology, allopatric speciation. It describes what happens when a single population of organisms gets geographically separated into two groups with no possibility of interbreeding. Over generations, they accumulate different mutations, adapt to different environments, and eventually diverge to the point where they can no longer reproduce with each other. They become separate species. The interstellar equivalent of allopatric speciation, call it cultural or even biological divergence across light-year separations, is not just possible. Given the timescales involved, it seems nearly inevitable. A colony established 1,000 light-years from Earth would, over the centuries and millennia of genuine isolation that light-speed communication enforces, become something genuinely different from whatever humanity started as. Not worse, not better, just different, irreversibly, profoundly different. The galaxy, if humanity ever spread across it, would not look like a human civilization. It would look like a tree, a trunk perhaps, at the origin point, branching into thousands of lineages that share a common ancestor but have grown in directions so divergent that the shared origin becomes more of a historical footnote than a lived identity. And that is, if everything goes well, that is the optimistic scenario. Now, here is a layer that the warp drive discussion almost never reaches, and I think it is one of the most important. We have been talking as if the destination is the problem, as if the challenge is getting there. But consider what happens to the civilization that stays behind. The ones who never leave, or who leave and return, or who build the infrastructure and watch others depart. Every time a warp-capable ship leaves for a distant star, it carries knowledge, culture, biology, and potential. It carries some fraction of humanity's accumulated wisdom and capability, and it disappears across a distance so vast that, for all practical purposes, it is gone. Not dead, gone. Unreachable in any meaningful conversational sense. The people who left are alive somewhere, doing things, learning things, perhaps making discoveries that would transform everything. But those discoveries will not reach home for decades or centuries. This creates what you might call a knowledge horizon problem. The total body of human knowledge, if humanity is spread across interstellar distances, becomes impossible to integrate. You cannot have a unified scientific community when the peer review process takes centuries. You cannot have a shared technological development when a breakthrough made at one node of civilization takes 100 years to reach another node, by which time that other node has independently arrived at a different solution or missed the breakthrough entirely and gone down a different path. Science, as we practice it, collaborative, cumulative, globally networked, building on the work of others in real time, would be structurally impossible across interstellar distances. Each node of civilization would develop its own science, its own technology tree, its own understanding of the universe. Branches of knowledge that started from the same roots would grow in directions that might become mutually incomprehensible over millennia. This is not pessimism. This is what the physics of communication speeds imply when applied honestly to the timescales of interstellar separation. There is no getting around it without something that does not currently exist, faster-than-light communication, and notably the Alcubierre warp drive, despite enabling what looks like faster-than-light travel, does not solve the communication problem for anyone who stays behind. The ship gets there fast. but it cannot send a message back any faster than light. Let us pull back even further, because there is a perspective on all of this that I think is easy to miss when you are deep in the physics and the sociology. And it is a perspective that I find genuinely moving. We are made of stardust. That is not a metaphor. It is chemistry. The carbon in your body, the oxygen in your lungs, the iron in your blood. These elements were forged inside the nuclear furnaces of stars that lived and died before our sun was born. A star somewhere between 5 and 10 billion years old. We do not know exactly which one or ones, fused hydrogen into helium, helium into carbon, carbon and helium into oxygen, and in its final moments of existence exploded in a supernova violent enough to synthesize the heavier elements and scatter them across space. Those scattered atoms eventually found their way into the molecular cloud that collapsed to form our solar system. They became rock, became ocean, became atmosphere, became life, became you. You are, in the most literal chemical sense, a child of the stars. The universe built you out of itself, and now you, we, are sitting on one small planet, looking out at the galaxy that made us, and trying to figure out how to go back. Trying to find a way to cross the void that separates us from the other furnaces, the other systems, the other places where the universe might have done something similar to what it did here. There is something profound about that drive, something that feels less like ambition and more like a kind of homecoming instinct operating at civilizational scale. We came from out there, in a sense, and something in us, in our science, our storytelling, our deepest curiosity, keeps pointing back out there. But the universe, in its indifference, has made the journey almost incomprehensibly hard. The same processes that built us also built the distances. The same physics that allows stars to burn allows the space between them to be effectively infinite on human timescales. The cosmos gave us the ingredients to wonder and the capacity to dream of crossing the void, and then made the void nearly impassable. That tension between the instinct to reach and the reality of the reach required is, I think, one of the most profoundly human things there is. We are the only species on this planet that knows about the distances and still wants to try, that knows the numbers and still builds telescopes, that understands the loneliness of the cosmos at a mathematical level and still looks up. Now, I want to introduce something that does not come up in most warp drive discussions, and it absolutely should. It is called the Cauchy horizon problem, and it is one of the reasons that some physicists who have spent the most time with the Alcubierre metric have quietly concluded that even if everything else were solved, the warp bubble might be fundamentally unstable at a quantum level. The Cauchy horizon, named after the French mathematician Augustin Louis Cauchy, is a type of boundary in space-time that appears in certain solutions to Einstein's field equations. It is a surface beyond which the predictability of physics breaks down. General relativity, on one side of a Cauchy horizon, can tell you exactly what will happen given initial conditions. On the other side, that predictability collapses. The equations become consistent with multiple different futures, which in the context of classical physics is deeply problematic. The interior of the Alcubierre warp bubble has a structure that, under detailed analysis, involves something closely analogous to a Cauchy horizon. The 2012 paper by Finazzi, Liberati, and Barcelo that we mentioned earlier in the context of radiation also addressed this. Their quantum field theory analysis found that the warp bubble would likely be quantum mechanically unstable. The vacuum fluctuations, the constant unavoidable quantum noise of empty space would be amplified by the geometry of the bubble in ways that could destabilize it catastrophically. What does catastrophic destabilization of a warp bubble look like? The honest answer is that we do not know precisely, because working out the full quantum gravity behavior of an Alcubierre spacetime requires a theory of quantum gravity that we do not yet have. general relativity and quantum mechanics, the two greatest theoretical achievements of 20th century physics, are famously incompatible with each other at a fundamental mathematical level. We do not have a working theory that unifies them. String theory and loop quantum gravity are the leading candidates, but neither has been experimentally confirmed in ways that would let us make definitive predictions about warp bubble stability. What we can say is that the classical picture of the warp bubble, the smooth, controlled, geometrically elegant picture from the original Alcubierre paper, likely does not survive intact when quantum effects are properly accounted for. Whether it collapses gracefully or catastrophically is an open question, but the naive expectation that you simply build the bubble, climb in, and ride it safely to your destination looks considerably less plausible once you go beyond classical general relativity. And this brings us to what I think is the deepest and most uncomfortable truth about warp drive, not as a physics problem, but as a philosophical one. We reached for it because the distances are too vast. We looked at the numbers, felt the weight of them, and thought there must be a shortcut. There must be a way to cheat the geometry, and general relativity, to its eternal credit as a theory, does not slam the door on that hope entirely. The Alcubierre metric is real. It is a legitimate solution to Einstein's equations. The universe at the mathematical level does not flatly forbid it. But the universe also does not make it easy. It does not make it clean. Every time physicists dig deeper into the warp drive concept, every time someone does a more rigorous analysis, adds a layer of quantum field theory, thinks through the causal structure more carefully, new problems emerge. Not insurmountable problems necessarily, but problems that compound, problems that pile up, problems that collectively paint a picture of a universe that is not hostile to the idea of faster-than-light travel exactly, but that has layered its barriers so deeply and so cleverly that they feel almost designed to prevent it. That might be meaningful, or it might just be the universe being the universe, indifferent, consistent, following its own rules without reference to what we would like. But either way, the pattern is worth noting. Every shortcut the cosmos seems to offer, when examined closely, turns out to require something we cannot have, or to create a consequence we cannot accept, or to depend on physics we have not yet unified. If warp drive is this fraught, if the physics creates this many interlocking problems at this many levels, then what are the alternatives? What does serious science actually say about how, if ever, a species might cross the void between stars, not through a shortcut in space-time, but through patience or cleverness, or some other approach that works with the universe's constraints rather than trying to bend around them? Because the answer to that question is not what you might expect. There are approaches being genuinely, seriously studied, real proposals, real mathematics, real missions, small ones, early ones, but real, that are beginning to explore whether crossing the distance between stars is possible without cheating the geometry. And some of them raise questions about what it means to be human that are, in their own way, just as unsettling as anything we have talked about today. If you are enjoying this journey, make sure to subscribe to the channel and give a like. Every day, there is new content going deep into astrophysics, cosmology, and the discoveries that are reshaping how we understand our place in the cosmos. There is a project that does not get nearly enough attention in mainstream science conversations, and it is one of the most audacious things our species has ever seriously attempted to plan. It is called Breakthrough Starshot, and it was announced in 2016 by a coalition that included the late Stephen Hawking, the Russian billionaire Yuri Milner, and the astronomer royal Martin Rees, three people who, between them, represent some of the most serious scientific and intellectual credibility on the planet. The proposal is this: build a fleet of tiny spacecraft, Not the kind of ship you picture when you imagine interstellar travel, not something with corridors and crew quarters and a bridge. These are gram-scale wafers, microchips with sails, each one roughly the size and weight of a postage stamp, carrying a miniaturized camera, a communication laser, and navigation systems etched into a surface smaller than your thumbnail. Attached to each one a light sail, an ultra-thin reflective membrane, perhaps a few meters across, and then illuminate that sail with an array of ground-based lasers so powerful that the tiny craft accelerates to roughly 20% of the speed of light within minutes. 20% of the speed of light is approximately 60,000 kilometers per second. For reference, the fastest human-made object ever launched, as of our current knowledge, reached speeds in the tens of kilometers per second during its closest solar approach, and that was considered a remarkable engineering achievement. 20% of light speed would be thousands of times faster than anything we have ever built. At that velocity, the journey to the nearest star system would take roughly 20 years. Not thousands of years, not millions, 20. And this is not science fiction. The physics are real. The engineering challenges are enormous, genuinely enormous, but they are engineering challenges, not fundamental physics barriers. The laser array required would need to be on the order of 100 gigawatts of combined power, which is roughly the output of 100 large power stations firing simultaneously at a single target. The light sail material needs to reflect nearly all of that energy without being destroyed by it, which requires materials science at the very edge of what is currently achievable. The tiny spacecraft need to survive decades of travel through the interstellar medium, where even nanometer-scale dust grains at 20% of light speed carry enough energy to be catastrophically damaging. These are hard problems, but they are problems that serious engineers are actively working on. Breakthrough Starshot has funded research, papers have been published, prototype components have been tested. This is not a thought experiment sitting in a drawer somewhere. It is a program with momentum, with funding, and with a roadmap. But here is what Breakthrough Starshot reveals about the nature of the distance problem and why it is relevant to our warp drive conversation. Even at 20% of the speed of light, the nearest star system is a 20-year journey for an unmanned probe the size of a postage stamp. What arrives at the destination is a tiny chip with a camera. It has perhaps minutes to take images and collect data as it flies through the target system at enormous velocity, with no ability to decelerate, because decelerating would require either a second laser array at the destination, which does not exist, or an onboard propulsion system, which would add mass that the current concept cannot accommodate. 20 minutes of flyby data after 20 years of travel. And then the images and measurements have to be transmitted back to Earth via that tiny onboard laser across the same distance, which means the data takes another 4+ years to arrive. So from launch to first data return, you are looking at roughly 25 years minimum for information about the nearest star system. And then you have learned what a postage stamp with a camera can tell you during a brief uncontrolled flyby at 1/5 of the speed of light. Now, scale that up. What would it take to send not a chip, but a human being? A human being requires food, water, atmosphere, protection from radiation, psychological support, medical care, and enough space to avoid complete psychological breakdown during a multi-decade journey. A human mission to even the nearest star system using anything resembling current or near-future technology, even something as advanced as the Breakthrough Starshot concept scaled up dramatically, would require a ship of enormous mass. And mass is the enemy of speed in a way that is almost mathematically merciless. The energy required to accelerate an object increases with both its mass and the square of its velocity. Double the mass, double the energy needed, double the speed, quadruple the energy needed. A crewed interstellar ship, even a minimal one, with a small crew, bare life support, and no luxuries, would be orders of magnitude heavier than a gram-scale light-sail probe. The energy to accelerate it to even a few % of light speed would be extraordinary. The energy to decelerate it at the other end, which the Starshot probes do not even attempt, would be equally extraordinary. This is why, when serious mission planners think about human interstellar travel without warp drive, they tend to arrive at a concept that is deeply strange by the standards of how we usually think about space exploration. They arrive at the generation ship. A generation ship is exactly what it sounds like. A vessel large enough to sustain a self-contained population, not just a crew, but a community, for the entire duration of an interstellar journey that might last decades, centuries, or even millennia, depending on the destination and the speed achievable. The people who board the ship are not the ones who arrive. Their children might not be the ones who arrive either. Their grandchildren, great-grandchildren, or descendants separated by 10 or 20 generations from the original crew might be the ones who finally see the destination star growing brighter in their view screens. The concept has been explored seriously in the scientific literature, not just in science fiction. A 2018 paper by Cameron Smith at Portland State University modeled the population genetics of an interstellar generation ship in genuine mathematical detail, working out how large a founding population would need to be to avoid the genetic bottleneck effects that come from small, isolated populations reproducing over many generations. The answer was sobering. To maintain adequate genetic diversity across a multi-century journey, the ship's founding population would likely need to be at least 10,000 individuals. Some analyses push that number higher, toward 40 or 50,000, when you account for the possibility of catastrophic mortality events during the journey. 10,000 people, minimum, possibly 50,000, on a ship that needs to sustain them for centuries. With food production, water recycling, atmosphere management, medical care, education, governance, culture, an entire civilization in a can, hurtling through the void, the engineering required is staggering. But the human dimension is what really makes you stop, think about what it means to be born on that ship. You did not choose to be there. Your parents were born there, and their parents before them. The destination is not a place you will ever see. It is a story told to you by elders, a destination your great-great-grandchildren might reach, an abstraction as distant from your daily reality as the ancient Earth your ancestors departed from. You live your entire life in a closed environment with the same few thousand people, going somewhere you will never arrive, for a purpose that was decided before you existed. What does identity mean in that context? What does purpose mean? What does freedom mean? These are not engineering questions. They are deeply human questions, and serious researchers in the field of long-duration space habitation, drawing on psychology, sociology, anthropology, and systems ecology, have found that they do not have clean answers. The psychological literature on isolation, on confined communities, on multi-generational trauma and purpose, suggests that sustaining a psychologically healthy population across the timescales a generation ship would require is at least as challenging as the engineering, possibly more so. There are analogies in human history: isolated island populations, remote monastic communities, long-duration polar expeditions, but none of them involve anything close to the timescales, the absolute closure, or the completeness of separation that an interstellar generation ship would entail. We are, in a meaningful sense, in genuinely uncharted psychological territory. And this is before we address the governance problem, which is enormous. Who decides the rules on a generation ship? The founding generation makes decisions about course, about resource allocation, about social structure. that bind every subsequent generation for centuries. Future generations had no voice in those decisions. They inherit a world, literally, the entire world available to them, shaped by people they never met, making choices they cannot revisit without potentially endangering the mission. This is a version of a problem that political philosophers have wrestled with in terrestrial contexts for centuries, the question of intergenerational justice. How much can one generation bind the next? On Earth, there are mechanisms for revision. Laws can be changed, constitutions can be amended, revolutions can happen. On a generation ship, certain decisions are effectively locked in. The trajectory is set. The life support systems are what they are. The genetic pool is what it started as. There is, in certain fundamental respects, no opting out. Some theorists have argued that this makes a generation ship mission ethically problematic in a way that is distinct from any other human adventure. We have always sent explorers into danger. We have always accepted that some missions will kill their crews, but those crews chose to go. The second generation on a generation ship, the first children born in transit, chose nothing. They are participants in a project that preceded their existence and that they cannot leave. That ethical tension does not make generation ships impossible, but it suggests that building one requires not just engineering solutions, but a level of social and philosophical wisdom that our species has not yet demonstrated at any comparable scale. Now here is the thing about all of this: the breakthrough Starshot probes, the generation ships, the physics of acceleration and deceleration and mass that I find most striking when I step back and look at the whole picture. Every realistic approach to interstellar travel that does not involve exotic, currently impossible physics ends up requiring either that we send something too small to be meaningful for human colonization, or that we accept timescales so long they strain the very concept of a continuous civilization. The fast approaches send chips, not people. The approaches that send people take so long that the civilization that sent them will have transformed beyond recognition by the time anyone arrives. Warp drive was supposed to be the escape from that dilemma, the way to be both fast enough and capable enough to actually matter as a tool of human expansion into the cosmos. And as we have spent this video establishing, the physics of warp drive, when examined seriously and honestly, introduces problems that are not obviously more solvable than the problems it was meant to solve, which leaves us in a genuinely strange place. Not hopeless. I want to be careful about that word, because hopeless implies the future is settled, and the future is never settled. But genuinely strange. Sitting on a planet, looking out at a galaxy containing somewhere between 100 billion and 400 billion stars, many of them orbited by planets, some of those planets almost certainly hosting conditions compatible with chemistry and perhaps with life, and being separated from all of it by distances that our best current physics cannot bridge cleanly. I want to tell you about something called the interstellar medium in a way that goes beyond the basic facts we covered in part 1. Because the interstellar medium is not just empty, it is actively hostile in ways that matter for any realistic mission concept. The space between stars is permeated by cosmic rays. These are not rays in the gentle, wave-like sense of visible light or radio signals. Cosmic rays are high-energy particles, protons, atomic nuclei, electrons, accelerated to enormous velocities by supernovae, by pulsars, by the violent processes surrounding black holes, and by other mechanisms we are still working to understand. They travel through the galaxy at energies that dwarf anything achievable in particle accelerators on Earth. The Earth's magnetic field and atmosphere protect us from the majority of cosmic ray bombardment. Remove that protection, send a crew into interstellar space for decades, and the radiation exposure becomes one of the defining challenges of the mission. Long-term cosmic ray exposure damages DNA, increases cancer risk, and, particularly concerning for extended missions, affects the brain. A 2018 study published in Scientific Reports, led by Charles Limoli at the University of California, Irvine, found that simulated cosmic ray exposure in animal models caused measurable neurological damage, cognitive impairment, anxiety-like behavior, synaptic degradation at doses relevant to long-duration spaceflight. This was not a theoretical extrapolation. It was direct experimental evidence of radiation-induced neurological harm. Shielding a crew from cosmic rays across an interstellar journey requires either enormous amounts of mass, which is the enemy of speed, or active magnetic shielding systems of a scale and power that have never been built. And even then, the most energetic cosmic rays, the ones physicists call ultra-high energy cosmic rays, carry enough energy that no practical shielding stops them completely. They pass through matter, they pass through planets. You cannot fully hide from them. The interstellar void is not just empty and cold and dark, it is radioactive. It is filled with fast-moving particles carrying energies sufficient to damage the biological machinery of living things. And any crew crossing that void for years or decades will be absorbing that damage continuously, with no way to fully prevent it. This is the picture that assembles itself when you look honestly at the challenge of reaching the stars, not a picture of impossibility. I want to be precise about that, because impossibility is a strong claim, and the history of science is littered with things that were called impossible before they were done, but a picture of profound, layered, interlocking difficulty, a picture of a universe that is not designed for biology to cross it easily, a universe whose architecture seems at every level of examination to enforce the isolation of its stellar systems against anything made of matter that wants to move between them. The distances are vast. The void is hostile. The timescales are civilization length. The physics of shortcuts produce their own barriers. The human cost, psychological, sociological, biological, of the journey is staggering even in the most optimistic scenarios. And yet, the stars are there. We know some of what is out there. We have found exoplanets by the thousands. As of the mid-2020s, the confirmed exoplanet count exceeded 5,500. Catalogued largely through missions like Kepler and TESS and confirmed by ground-based follow-up observations. We have found rocky planets in the habitable zones of nearby stars. We have detected atmospheres around worlds dozens of light-years away. We are building instruments, the James Webb Space Telescope being the most powerful currently operational, that are beginning to read the chemical fingerprints of those distant atmospheres, searching for molecules that would suggest biological activity. We are finding, in other words, that the destinations are potentially worth the journey, that the universe is not just vast and hostile and lonely, it is also extraordinarily full of places, full of possibilities, full of the raw materials that here on Earth assembled themselves into something that could eventually wonder about them from far away. There is a thought that has been circulating quietly among astrobiologists, futurists, and theoretical physicists for several decades now, and it tends to make people uncomfortable the first time they really sit with it. It goes like this. The biological human body, the one that evolved over roughly 3.8 billion years of life on Earth, optimized for a one-gravity environment, a nitrogen-oxygen atmosphere, ambient temperatures between roughly 0 and 40 degrees Celsius, and a lifespan measured in decades, might simply be the wrong vessel for interstellar travel. Not inadequate in a way that better engineering can fix, wrong in a more fundamental sense. Wrong the way a fish is wrong for climbing a tree, not broken, just shaped for a different environment entirely. This is not a fringe position, it is a conclusion that follows naturally from the numbers. A biological human body requires food, water, breathable air, sleep, social interaction, medical care, protection from radiation, and a psychologically sustainable environment. All of those requirements add mass, complexity, and fragility to any mission, and at interstellar distances, fragility compounds over time in ways that become existential. The journey is simply too long, too hostile, and too isolated for a body that was never designed for it. So the question that serious researchers in long-duration spaceflight, astrobiology, and the philosophy of mind have increasingly been asking is not how to protect a biological human body during an interstellar journey. It is whether the traveler needs to be biological at all. Let us be precise about what this actually means, because it is easy to slip into science fiction territory here and lose the thread of what is genuinely being discussed in scientific and philosophical literature. There are roughly 3 distinct ideas being explored under this umbrella, each with different implications and different levels of current plausibility. The first is what might loosely be called directed panspermia of information, sending not living beings but the information required to reconstruct them, compressed genetic data, developmental blueprints, cultural archives, scientific knowledge. A probe, potentially something like a more advanced version of the breakthrough Starshot concept, travels to a destination star system and, upon arrival, uses local materials to construct biological life from the information it carries. No biological passengers need to survive the journey. The journey is made by data, which is far more robust than flesh, and the biology is reconstructed at the destination. This idea has been discussed seriously in the astrobiology literature. It sounds like science fiction, but the underlying concept that the information in DNA is separable from the physical substrate that carries it, and that in principle that information could be transmitted and used to bootstrap biology somewhere else, is grounded in real molecular biology. Whether it is practically achievable is a different question, one that runs into enormous technical obstacles around the complexity of constructing viable biological organisms from scratch in an alien environment. But the conceptual framework is legitimate. The second idea is digital consciousness transfer, the notion that if human consciousness can be understood as a pattern of information processing in a physical substrate, then in principle that pattern could be copied, transmitted, and run on a different substrate at the destination. Send the pattern, not the person. Reconstruct the mind in a new body, biological or synthetic, at the other end. This idea is philosophically controversial in ways that the first is not, because it runs directly into some of the deepest, unsolved problems in philosophy of mind. Is consciousness substrate independent? Is a copy of a mind the same mind, or a different one that merely believes it is continuous with the original? What happens to personal identity across a copying process? These are not questions science has answered. They are questions science does not yet have the tools to address rigorously, because we do not have a scientific theory of consciousness that resolves them. But the idea is being taken seriously, not as an imminent technology, but as a long-run possibility that some researchers believe could be more achievable on long enough timescales than solving the engineering problems of biological interstellar travel. The third idea is perhaps the most grounded in near-term extrapolation. It involves sending artificial intelligence, not a copy of a human mind, but a genuinely non-biological intelligence, as the primary agent of interstellar exploration and perhaps settlement. An artificial mind does not need food or water or atmosphere. It does not experience loneliness in the biological sense. It does not accumulate radiation damage in the way biological tissue does, though its hardware would need protection. It does not have a lifespan measured in decades, and it can, in principle, be paused, put into a low-power state during the long transit, and reactivated upon arrival. in a way that a biological being cannot. This is the most straightforward of the three ideas in terms of physical plausibility, and it is the one that researchers like the late Marvin Minsky at MIT, Ray Kurzweil, and many others in the artificial intelligence and cognitive science communities have written about most extensively, not as a replacement for humanity, but as a complement, an extension of human agency into environments and across timescales where biological humans simply cannot go. Now here is where this conversation gets philosophically interesting in a way that I think touches something very deep. If the beings who eventually cross the interstellar void are artificial intelligences, or digitally reconstructed minds, or biologically engineered post-humans optimized for multi-century journeys, in what sense are they us? In what sense does humanity expand to the stars, rather than something descended from humanity, or inspired by humanity, or built by humanity? This is not a trivial question. It is arguably the central question of any serious, honest conversation about the long-term future of our species in the cosmos, because one answer is, it does not matter. If something that originated from human knowledge, human values, human curiosity, and human creativity successfully crosses the void and establishes a presence around another star, then in some meaningful sense humanity has reached the stars. The torch has been carried. Even if the torchbearer looks nothing like the person who first lit it, another answer is, it matters enormously. If what we send is so different from what we are, so transformed by the requirements of the journey that it no longer shares our biology, our mortality, our social bonds, our lived experience, then we have not sent ourselves anywhere. We have sent something else, something new, and the humans who remain on Earth are still trapped here, separated from the stars by the same impassable void, having perhaps created successors capable of crossing it, but not having crossed it themselves. There is no consensus answer to this. It is a question that sits at the intersection of philosophy of mind, ethics, and the sociology of the future in a place where genuine resolution is not currently possible. I raise it not to resolve it, but because I think it is important to name it clearly. Because the conversation about interstellar travel, when it is honest, is not just a conversation about propulsion or energy or distance. It is a conversation about what we are, what we want to preserve of what we are, and what we are willing to transform into in order to reach further. Let us bring this back to something concrete, because I do not want to lose the thread of the physical reality in the abstraction of philosophy. There is one more propulsion concept worth discussing that sits between the fantasy of warp drive and the slow patience of generation ships, and it has a history that makes it one of the most fascinating episodes in the story of human ambition meeting physical reality. It is called Project Orion, and unlike warp drive, it required no exotic matter, no negative energy density, and no physics beyond what was already confirmed in the 1950s. It was real engineering designed by real people with clearance levels and government funding, and it was cancelled not because it did not work, but because of a treaty. The concept was developed in the late 1950s and early 1960s, primarily at General Atomics in California, by a team that included some of the most brilliant physicists of the era, among them Freeman Dyson, whose name you may recognize from the Dyson sphere concept, and Stanislaw Ulam, one of the co-inventors of the hydrogen bomb. The idea was breathtakingly simple in principle. Take a large spacecraft, attach to its rear a thick metal plate, the pusher plate, mounted on shock absorbers. Eject small nuclear bombs out the back of the ship, one at a time, and detonate them. The plasma from each detonation hits the pusher plate and accelerates the ship. Repeat, thousands of times. It sounds absurd. It is also, from a purely physical standpoint, one of the most energy-dense propulsion concepts ever seriously proposed. Nuclear explosions release energy at a power density that chemical rockets cannot remotely approach. A ship propelled by nuclear pulse detonation could, in principle, achieve velocities of several % of the speed of light with a large enough supply of bombs. Dyson himself estimated that a true interstellar Orion, a ship designed for a journey to another star system, could reach roughly 3% of light speed. At that velocity, the journey to the nearest star system would take roughly 140 years. Not a quick trip, but not millions of years either. The program was cancelled in 1963 following the Partial Nuclear Test Ban Treaty, which prohibited nuclear detonations in space. The people who worked on it, Dyson especially, maintained for the rest of their lives that it was a genuine loss. That the treaty, whatever its justifications in the context of the arms race, had closed off a path to the stars that was physically real and technically achievable. Whether that is true is a complicated question. The engineering challenges of an actual interstellar Orion, even accepting the basic concept, were enormous. The radiation exposure to the crew from thousands of nuclear detonations immediately behind the ship would have been severe. The shock absorption required to make the ride survivable at scale stretched the limits of known materials science, and the political and ethical dimensions of launching a ship carrying thousands of nuclear weapons through Earth's atmosphere were not trivial. But the point stands. Orion was not fantasy, it was engineering. Rough, dangerous, politically fraught engineering, but engineering grounded in confirmed physics. And it reminds us that the solution to the interstellar distance problem, if it comes, will probably not look like what we imagine. It will probably be stranger, more surprising, and more morally complex than the clean, elegant narrative of a warp drive cutting effortlessly through space. There is something called the rocket equation that I want to talk about here, because it is one of those pieces of physics that sounds dry and technical until you really understand what it implies. And then it becomes one of the most humbling equations in science. The Tsiolkovsky rocket equation, named after the Russian scientist Konstantin Tsiolkovsky, who derived it in 1897, describes the relationship between a rocket's change in velocity, the velocity of its exhaust, and the ratio of its initial mass to its final mass. It tells you, essentially, how much fuel you need to achieve a given change in velocity. The brutal implication of this equation is that the fuel required grows exponentially with the desired velocity change, not linearly, exponentially. If you want to go twice as fast, you need much more than twice as much fuel, because you also have to accelerate the fuel itself, and then you need fuel to accelerate that fuel, and the fuel to accelerate that fuel. The equation compounds on itself in a way that becomes almost mathematically sadistic at high velocities. For a chemical rocket, like the ones currently used to launch payloads into orbit, the exhaust velocity is roughly 4.5 kilometers per second. To reach even 1% of the speed of light, 3,000 kilometers per second, using chemical propulsion, the mass ratio of fuel to spacecraft would be so astronomically large that it is physically impossible. You would need more mass in fuel than exists in the observable universe many times over. Even nuclear propulsion, with exhaust velocities perhaps 100 times higher than chemical rockets, faces brutal constraints from the rocket equation at the velocities needed for meaningful interstellar travel. Getting to 10% of light speed with a nuclear rocket requires a mass ratio in the thousands, meaning the fuel outweighs the spacecraft payload by a factor of thousands to 1 at launch. This is why concepts like breakthrough Starshot, which bypass the rocket equation entirely by using an external laser rather than onboard fuel, are so appealing to physicists. The laser stays at home. The ship carries no fuel. The rocket equation does not apply in the same way. But the trade-off is that you lose the ability to decelerate which means you cannot stop at the destination, which means you cannot land, which means you cannot establish a presence. You can only fly through. Every approach to interstellar travel, when examined honestly through the lens of real physics, reveals a trade-off that cannot be entirely eliminated. Speed versus mass, deceleration versus fuel, biology versus robustness, human presence versus practical achievability. The universe does not offer a free lunch. Every step toward the stars comes with a cost that bends back toward the same fundamental constraint. The distances are simply, almost cosmically, too vast for the tools we have. Here is where I want to land at the end of Part 5, before we go deeper in Part 6, into the question that I think ultimately reframes this entire conversation. We have spent 5 parts now looking at warp drive from every serious angle: the physics, the energy, the exotic matter, the radiation, the causal isolation, the quantum instability. And alongside that, we have looked at the realistic alternatives: the light sail probes, the generation ships, the nuclear pulse drives, the possibility of sending something other than biological humans. And in each case, the same picture assembles itself. The distances win, not always completely, not always permanently, but they win in the sense that every solution comes with a cost that keeps the stars at arm's length in one way or another. Either the journey is too slow for any individual human life to span, or the journey is fast enough but sends something too small to matter for civilization, or the journey requires transforming the traveler so fundamentally that the original question, "Can humans reach the stars?" quietly changes its meaning mid-sentence. But here is what I have not told you yet. Here is the layer of this conversation that I think changes everything, not by making the problem easier, but by reframing what the problem actually is. The question is not really whether we can cross the distance. The question is whether crossing the distance is the right frame at all, because there is something else the stars are giving us right now without any travel required. Something that the latest generation of telescopes and observatories is beginning to deliver at a rate that would have been unimaginable even 20 years ago. And it suggests that the relationship between humanity and the stars might not depend on crossing the void as much as we have always assumed. On the 18th of December 2021, a rocket lifted off from the Kourou launch site in French Guiana, carrying what many astronomers consider the most important scientific instrument humanity has ever built: the James Webb Space Telescope, a machine so sensitive that it can detect the heat signature of a bumblebee at the distance of the Moon, a mirror so large, 6.5 meters across, assembled from 18 gold-coated hexagonal segments that it had to be folded origami style to fit inside its launch vehicle and then unfurl in space over the course of 2 weeks in a sequence of 344 individual deployment steps, every single one of which had to work correctly or the mission would fail. It worked, all 344 steps. And what it has been showing us since, what it continues to show us with every new observation campaign, is something that quietly, fundamentally shifts the conversation about humanity's relationship with the stars. Because the James Webb Space Telescope is not just taking pretty pictures. It is reading atmospheres. It is detecting the chemical fingerprints of worlds dozens of light years away, breaking down the starlight that filters through their atmospheres during transits, those brief moments when a planet passes between its star and us, and identifying which molecules are present. Water vapor, carbon dioxide, methane, sulfur dioxide, molecules that in certain combinations and concentrations would tell us something extraordinary about the world that hosts them. In 2023, Webb detected carbon dioxide and water vapor in the atmosphere of the exoplanet WASP-39b, a gas giant roughly 700 light-years away. That same year, tantalizing signals, still under intense scientific scrutiny, and not yet confirmed as of the time of this recording, emerged from observations of K218b, a sub-Neptune world roughly 120 light-years from Earth, orbiting in the habitable zone of its star. The signals included what appeared to be the spectroscopic signature of dimethyl sulfide, a molecule that, on Earth, is produced almost exclusively by marine phytoplankton, biological organisms, life. Let me be careful here. The K218b result is not confirmed. The signal is real, the data is real, but its interpretation is actively debated among astrobiologists and atmospheric scientists. There are abiotic processes not involving life that might produce similar signals. The science is ongoing. No one is claiming we have found life. What we are claiming is that we have detected a molecule at a distance of 120 light-years that on Earth is a biosignature. That we are now capable of having that conversation at all, that we are now doing the chemistry of worlds more than 100 light-years away from our telescopes, is the point. 20 years ago, we could not do this. 10 years ago, we could barely imagine doing it this well. Today, we are doing it, and the James Webb Space Telescope is only in the early years of its operational life. This is the reframing I mentioned at the end of Part 5. And I want you to feel the full weight of what it means. For most of human history, the stars were lights, points of brightness in the dark, separated from us by voids we could not cross and distances we could not measure. Our relationship with them was aesthetic, navigational, mythological. We told stories about them. We used them to find our way. But we knew nothing of what they actually were. And the idea that we might one day know whether life existed around them would have seemed not just impossible, but almost presumptuous. Then came the age of telescopes. We learned the stars were other suns. We measured their distances. We understood their physics. We began to suspect that some of them hosted planets. In 1995, Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in France, confirmed the first exoplanet orbiting a Sun-like star, 51 Pegasi b, a gas giant roughly 50 light-years away. That discovery earned them the Nobel Prize in Physics in 2019, and it cracked open a door that has not stopped swinging wider since. Today, as of the mid-2020s, we have confirmed more than 5,500 exoplanets. The Kepler Space Telescope alone, during its 9-year mission, found roughly 2,700 of them. Its successor, the Transiting Exoplanet Survey Satellite, TESS, has added thousands more. We have found planets smaller than Earth, planets larger than Jupiter, planets in binary star systems orbiting 2 suns simultaneously, planets in the habitable zones of their stars, the regions where liquid water could, in principle, exist on a surface. We have found, in other words, that planets are not rare, they are the default. Almost every star we look at with sufficient sensitivity appears to host at least one planet. The galaxy is not a sparse scattering of isolated suns, it is a forest of solar systems, each one a potential story, each one a potential somewhere. And the James Webb Space Telescope is now beginning to read those stories from here, without crossing the void, without a warp drive, without a generation ship, from a vantage point 1.5 million kilometers from Earth, orbiting the second Lagrange point of the Sun-Earth system. A telescope is having conversations with the atmospheres of worlds 100 light-years away. Now, I want to be honest about the limits of what telescopes can tell us, because this reframing is real and important, but it is not a complete substitute for the thing it reframes. Spectroscopy, the technique Webb uses to analyze atmospheres, tells us what molecules are present in bulk. It does not tell us what the surface looks like. It does not tell us whether there are oceans, continents, weather, seasons, cities. It does not tell us whether the life, if it exists, is microbial or complex. It cannot show us a face, it cannot play us a sound. It cannot convey the texture of an alien shore or the color of an alien sky with any resolution that approaches what a camera in orbit around that world could provide. There is a profound difference between knowing something and experiencing it, between detecting a biosignature at 120 light-years and standing on the surface of the world that produced it. Telescopes can tell us whether a world is potentially interesting. They cannot tell us what it is like to be there. And there is something in human nature, something deep and persistent and arguably inseparable from what curiosity actually is, that wants not just to know but to go. Carl Sagan captured this beautifully in his 1994 book Pale Blue Dot, where he wrote about the human compulsion to move, to wander, to cross borders and see what lies beyond them. He traced it through our evolutionary history, the migrations out of Africa, the settling of every continent, the crossing of oceans in vessels that were, by any rational assessment, inadequate for the task. He argued that this restlessness is not a flaw but a feature, that it is, in a deep sense, what we are. If that is right, then no telescope, however powerful, will ultimately satisfy the part of us that wants to go. It will feed our curiosity, it will deepen our knowledge, it will perhaps identify destinations so compelling that the impossibility of the journey becomes harder to accept rather than easier. But it will not replace the journey. This tension between knowing and going, between the intimacy of telescope data and the irreplaceable experience of presence, sits at the heart of the human relationship with the cosmos. And I think it is worth naming clearly, because it is easy to let the remarkable achievements of observational astronomy paper over the fact that we are still here, still separated, still looking from a distance that no current technology can meaningfully close. Let us talk about something that does not come up enough in popular discussions of this topic, and that is the question of what we are actually looking for when we look at other worlds, what we mean when we say we are searching for life. The search for life beyond Earth, astrobiology, as the field is formally known, is one of the fastest growing areas of scientific research in the world right now. It draws together astronomers, chemists, geologists, biologists, and physicists in a collaboration that would have been hard to imagine a generation ago. And one of the things that collaboration has produced is a much more nuanced and expansive definition of what life might look like. For a long time, the implicit model of extraterrestrial life in the scientific community, let alone in the popular imagination, was essentially Earth life with cosmetic variations, different biochemistry perhaps, different morphology, but broadly operating on the same principles, carbon-based, water-dependent, requiring certain temperature ranges. The Drake equation, formulated by astronomer Frank Drake in 1961 as a way of estimating the number of communicating civilizations in the galaxy, encodes a lot of these assumptions in its variables. It is fundamentally an equation about life like us, but the biochemical possibilities are far stranger and far wider than Earth life suggests. Silicon has some of the same bonding properties as carbon and has been proposed as a potential alternative basis for complex chemistry under very different temperature conditions. Ammonia has been proposed as an alternative solvent to water in cold environments. Hydrogen fluoride could theoretically serve as a solvent at even lower temperatures. Life based on completely different chemical architectures, not just different DNA but different fundamental molecules, is not ruled out by physics or chemistry. It is simply unexplored. This matters for the interstellar distance conversation in a subtle but important way. If life in the universe is far more biochemically diverse than Earth life, if the definition of what counts as alive is broader than our current models, then the fraction of star systems hosting life might be higher than the most conservative estimates suggest. And if that is true, then the destinations out there, the worlds the James Webb Space Telescope is beginning to probe, are potentially even more interesting than the already remarkable possibility of finding something like us. The universe might be more alive than we know, not in a mystical sense, in a strictly chemical, physical, biological sense, teeming not with creatures that look like us or think like us, but with chemistry that is doing something that by any rigorous definition deserves to be called living. There is a concept in astrobiology called the cosmic habitable age, the idea, developed by researchers including Charles Lineweaver at the Australian National University, that there is a window of time in the universe's history during which the conditions for complex life are most favorable. Too early in the universe's history, and there were not enough heavy elements, the carbon, oxygen, nitrogen, iron, and other elements forged in stellar interiors and distributed by supernovae to build the kind of chemistry life as we know it requires. The first generation of stars were made almost entirely of hydrogen and helium. They had to live and die, seeding space with heavier elements before life had the raw materials it needed. Too late, on timescales of tens of billions of years, and the universe will have changed in ways that may be less hospitable. Stars will be dimmer and cooler on average. The processes that recycle material through galaxies will have slowed. The cosmic environment will be different in ways we cannot fully predict. We appear to live in approximately the right era, not at the very beginning of the cosmic habitable age, but well within it. The universe is roughly 13.8 billion years old, and Earth formed about 4.5 billion years ago, late enough for plenty of heavy element enrichment, early enough to have billions of years of stellar stability ahead. What this means, and what researchers like Lineweaver and others have pointed out, is that if life tends to emerge wherever conditions allow it, then there may be worlds out there that are older than Earth, significantly older, worlds where life has had not 4 billion years to develop but 6 billion, 8 billion, 10 billion, worlds where evolution, assuming evolution is the mechanism at work, has had dramatically more time to produce complexity. If complex life exists on such worlds, what might it look like after 6 billion years of evolution relative to our 4? We have had roughly 500 million years of complex multicellular life on Earth. 6 billion years of complex life is 12 times that span. The cognitive and technological gulf between us and whatever might exist on such a world, if it exists, could be incomprehensibly vast. This connects back to the Fermi paradox in a way that is worth noting. Where is everyone? If the galaxy is full of worlds, some of them much older than ours, where are the signs? We have been listening with radio telescopes since Frank Drake pointed a dish at 2 nearby stars in Project Ozma in 1960. We have scanned millions of stars. We have heard nothing unambiguously artificial. The silence is itself data. It means something. We do not know what it means. The proposed explanations range from the sobering to the terrifying, but it is real data, and any honest conversation about the stars has to include it. Now, here is a possibility that I find both humbling and strangely beautiful, and that connects directly to the distance problem we have been exploring throughout this video. What if the silence is partly a consequence of the distances themselves? What if civilizations do arise in many places across the galaxy and do reach a level of technological sophistication that allows communication across interstellar distances, but that the vast separations between stars mean that any two civilizations capable of communicating are still, by the time they develop that capability, so far apart that their signals have not had time to reach each other yet. The galaxy is 100,000 light-years across. A signal sent from one side takes 100,000 years to reach the other. If civilizations are spread thinly, even one per every few hundred light-years, then the time for their signals to mutually arrive could easily exceed the current age of any individual civilization. We might be surrounded by conversations we cannot yet hear, not because they are not happening, but because the speed of light has not yet delivered them to our doorstep. The universe might be full of voices calling out into the dark, each one broadcasting into a void so vast that the echoes have not come back yet. Each civilization alone, not because it is truly alone, but because the distances impose a silence that looks the same as absence. If that is even partially true, it does not make the distances less daunting, but it makes the loneliness feel different, less like an empty universe, and more like a universe of isolated lights, each burning bravely in a darkness too vast for any of them to know the others exist. And that image of lights in the dark, separated by distances that dwarf any technology we have yet imagined, each burning without knowledge of the others, is, I think, one of the most honest pictures of the cosmos we currently have. We have established that the distances are almost incomprehensibly vast. We have established that warp drive, for all its mathematical elegance, introduces problems that may be as deep as the ones it solves. We have established that realistic alternatives, generation ships, light sail probes, nuclear pulse drives, each come with costs that keep the stars at arm's length in one way or another. We have established that the traveler of the future might need to be something other than a biological human. And we have established that telescopes are beginning to show us the stars in ways that were unimaginable a generation ago, without requiring us to cross the void. But there is one more dimension to this conversation that we have not addressed yet, and it is the one that I think should matter most to you, personally, as someone alive right now, in this particular moment of cosmic and human history, because right now, in the span of a single human lifetime, the tools we are building, the missions we are flying, the observations we are making are not just incrementally advancing our knowledge of the stars. They are approaching, for the first time in history, the threshold of being able to answer the question, not whether we can reach the stars, but whether we are alone, and the implications of either answer, yes, we are alone, or no, we are not, are so profound, so civilization reshaping, so philosophically radical that understanding them requires its own conversation. Let us start with a number, not a distance this time, not a velocity, just a number sitting quietly in the middle of one of the most consequential scientific debates of our era. 1. That is the number of planets we know with absolute certainty hosts intelligent life. 1. This one, Earth, a rocky world, third from a medium-sized star on the outer edge of one of the Milky Way's spiral arms, orbiting unremarkably in a galaxy containing somewhere between 100 billion and 400 billion other stars, in a universe containing somewhere between 100 billion and 2 trillion other galaxies. One confirmed example of intelligent life in all of that. Now, here is the question that cuts to the heart of everything this video has been building toward. Is that one a statistical anomaly, a fluke so improbable that it may genuinely be unique in the observable universe? Or is it simply the first data point in what will eventually reveal itself to be a densely populated cosmic ecosystem, where the silence we currently experience is a consequence of the distances and the timescales, not of genuine emptiness? The answer to that question, whichever direction it falls, does not just affect the science of astrobiology. It does not just affect the philosophy of our place in the universe. It affects, in a very direct and practical sense, how we should think about the interstellar distance problem, because the value of crossing the void depends enormously on what is on the other side. Let us think carefully about the two possibilities, because both of them, when you follow them honestly to their logical conclusions, lead somewhere deeply strange. The first possibility is that we are alone, or very nearly alone, that the emergence of intelligent, technologically capable life is so improbable, requiring such a specific and unlikely sequence of events, that it has happened only once, or perhaps a handful of times in the entire observable universe. This position has serious scientific support. It is associated most prominently with what is called the rare Earth hypothesis, developed and named in a book by paleontologist Peter Ward and astronomer Joe Kirschvink, and earlier by Ward and Donald Brownlee, published in 2000. The argument goes roughly like this. The conditions that allowed complex life to emerge on Earth are not just favorable, they are extraordinarily specific. The right distance from the right kind of star, a large moon stabilizing the planet's axial tilt, a giant outer planet, Jupiter, acting as a gravitational shield, deflecting or capturing many of the comets and asteroids that would otherwise sterilize the inner solar system with constant impact events, plate tectonics recycling nutrients and regulating atmospheric carbon dioxide, a magnetic field protecting the surface from the solar wind. Each of these factors individually seems like a detail. Together, their coincidence in a single system looks less like luck and more like an extraordinarily narrow set of requirements. If the rare Earth hypothesis is correct, if complex, intelligent life is genuinely rare, then the interstellar distances take on a different kind of weight. They are not just barriers to exploration, they are barriers between almost nothing and almost nothing else. The void between stars is not separating us from a crowded cosmos full of neighbors. It is separating individual islands of improbable complexity in an ocean of chemical simplicity. In that universe, crossing the void matters enormously, because every example of complexity, every world that against enormous odds produced something capable of asking questions, is cosmically precious. And losing any of them to isolation or extinction would be a loss that the universe might never recover from. The second possibility is the one that most people instinctively prefer, and I think it is worth examining why. The possibility that we are not alone, that life, even intelligent life, is widespread in the cosmos, that the galaxy is, in some sense we have not yet been able to confirm, inhabited. This possibility is also scientifically grounded. The chemistry of life, carbon chemistry, amino acids, nucleotides, the basic building blocks, is not rare in the universe. Amino acids have been found in meteorites. Complex organic molecules have been detected in interstellar clouds. The Murchison meteorite, which fell in Australia in 1969, contained more than 90 different amino acids, only 19 of which are found in life on Earth. The raw materials of biology are scattered across the cosmos by the same stellar processes that built us. The argument from chemistry says this: if the ingredients are widespread, and if given the right conditions, chemistry tends to organize itself into increasingly complex structures, a process sometimes called abiogenesis, whose details are still deeply contested, but whose broad outline is supported by laboratory experiments, then life may be not just possible but probable across a wide range of environments. The universe may be, in a chemical sense, predisposed toward life. If this is true, the galaxy may contain not just microbial life, which most astrobiologists consider plausible given the chemistry, but intelligent life, civilizations, perhaps many of them, perhaps some that are millions of years more advanced than us. And yet we see nothing, we hear nothing, we detect nothing unambiguously artificial in our observations of the sky. The silence is complete. And that silence in a universe that might be teeming with life demands an explanation. This is the Fermi paradox, stated in its sharpest form. If they exist, where are they? And the proposed solutions to it range from the mundane to the deeply unsettling. Some of the solutions are optimistic. Perhaps intelligent civilizations are widespread but simply have not reached us yet. Perhaps the distances and the timescales make contact statistically unlikely, even in a populated galaxy, for reasons we touched on in Part 6. Perhaps everyone is listening and no one is transmitting, caught in a cosmic version of two people waiting for the other to speak first. Perhaps the signals are there, but we have been looking in the wrong frequency bands, or with inadequate sensitivity, or for too short a time. We have been systematically searching for extraterrestrial signals for roughly 60 years. On a cosmic timescale, that is the blink of an eye. Some of the solutions are neutral. Perhaps intelligent civilizations exist, but choose not to broadcast. Perhaps they go radio silent for reasons of security or privacy, or because they have moved beyond radio communication to technologies we cannot yet detect. Perhaps they have explored the galaxy but found nothing worth stopping at in our corner of it. Perhaps the concept of interstellar communication or travel is simply not a priority for most civilizations for reasons that would make sense to them, but that we cannot currently imagine. And some of the solutions are deeply sobering. Perhaps intelligent civilizations reliably destroy themselves before they can reach the level of interstellar communication. This idea, the Great Filter, was articulated by economist Robin Hanson in 1998. The argument is that something in the sequence of steps from simple chemistry to interstellar civilization is extraordinarily difficult, so difficult that almost no species makes it through. And the filter might be behind us, meaning the hard part was getting to where we already are. Or it might be ahead of us, meaning what kills civilizations is something we have not yet encountered. The discovery of life, even microbial life, elsewhere in the universe, would have profound implications for which version of the Great Filter story is true. If life arose independently on Mars, or on one of Jupiter's moons, or in the atmosphere of a distant exoplanet, that would suggest the emergence of life from chemistry is not the rare step, which means the filter, if there is one, must lie somewhere further along the path, somewhere between simple life and the kind of civilization that can cross the stars, somewhere perhaps close to where we currently stand. That is a thought worth sitting with for a moment. Now let me bring this back to the distance problem in a way that I do not think gets enough attention. There is a deep irony at the heart of the interstellar travel conversation, and it goes like this. The scenarios in which interstellar travel is most urgently needed are also the scenarios in which it is hardest to justify the cost, and the scenarios in which it is easiest to justify, where the destinations are known to be interesting, where there is something specific to go to, are the ones in which our current inability to cross the void is most acutely felt. Let me unpack that. If we are alone, if the rare Earth hypothesis is correct and complex life is vanishingly rare, then the primary reason to reach the stars is not to find neighbors, it is to spread, to ensure that whatever improbable thing happened here does not end here, to make life and consciousness and curiosity a multi-stellar phenomenon so that no single catastrophe, no asteroid, no nearby supernova, no civilizational collapse can erase it entirely. In that scenario, interstellar travel is existential insurance. It is the answer to the cosmic fragility of being the only thing in the universe capable of understanding the universe. And the distances in that context are not just a technical problem, they are an existential threat. Every year we remain a single planet species is a year in which everything we are, every piece of knowledge, every work of art, every love and grief and question and breakthrough is stored on one small rock, vulnerable to a single bad event. The astronomer Carl Sagan and the physicist Stephen Hawking both made versions of this argument in their public work, not as science fiction speculation, but as a sober assessment of long-term civilizational risk. Single-planet species are, on cosmic timescales, temporary. The only path to permanence, the only way for life and intelligence to become a durable feature of the universe rather than a brief spark, is to spread beyond the fragile confines of a single world. But spreading beyond a single world, spreading beyond the solar system, means crossing those distances, those 40 trillion kilometers of void, those light years that break warp drives and shatter generation ships, and defeat even the most carefully engineered propulsion concepts currently on our drawing boards. The urgency and the difficulty are in exact proportion. The more you believe the single-planet risk is real, the more the distances seem like an unbearable obstacle. But here is the other side of the irony. The scenario in which crossing the void is easiest to justify practically, not existentially but in terms of scientific and civilizational motivation, is the scenario in which we find something out there. A biosignature confirmed, a signal detected, evidence, however indirect, that there is something at a particular destination that merits the extraordinary investment of an interstellar mission. In that scenario, the destination is known, the purpose is clear, the motivation, scientific, philosophical, perhaps even species-defining, is overwhelming. Humanity would have found its most important question answered partially, and the only way to answer it fully would be to go. And yet, if that discovery comes from a world 100 light-years away, the distances are exactly as vast as they always were. The physics does not care about our motivation. The exotic matter requirements of the Alcubierre drive do not shrink because we have found a biosignature. The radiation problem does not solve itself because we desperately want to know more. The Tsiolkovsky rocket equation does not become more forgiving because the destination is now interesting. The universe has constructed a situation in which the more we learn from here, the more our telescopes reveal about what is out there, the more urgently we want to go, and the more acutely we feel the impossibility of getting there quickly. It is as if the cosmos has designed a particular kind of exquisite frustration for any species intelligent enough to understand the distances and curious enough to want to cross them. There is a concept in philosophy sometimes called epistemic humility, the intellectual virtue of being honest about the limits of what you know, and I want to apply it here carefully because I think this conversation risks sliding into a false certainty in either direction. We do not know that warp drive is impossible. We know it is enormously difficult. We know the obstacles are real and deep, but the history of physics is full of things that were considered impossible until they were not. Heavier than air flight, nuclear energy, quantum computing, the laser, the transistor, each of these, at some point in the history of science, was either considered impossible or was not yet imaginable. The history of human ingenuity is a history of collapsing impossibilities. At the same time, we should not let optimism about human ingenuity paper over the specific, detailed, well-grounded reasons why crossing the distances between stars is hard. This is not like saying powered flight is impossible because birds flap their wings and we cannot. This is like saying powered flight is impossible because there is no air, a constraint that cannot be engineered around, only worked within. The distances are real. The physics is real. The constraints that arise from both, the communication delays, the energy requirements, the biological fragility, the causal structure of space-time, are real. Respecting that reality does not make you a pessimist. It makes you honest. And honest engagement with the problem is the only foundation on which real progress can be built. What I find most striking when I step all the way back and look at this conversation from the widest possible angle is this: we are a species that has existed in our current form for roughly 300,000 years. We have had writing for roughly 5,000 years. We have had science, in anything like the modern sense, for roughly 400 years. We have had spaceflight for less than 70 years. We have had exoplanet science for less than 30 years. And in that extraordinary eye blink of cosmic time, we have gone from not knowing whether other planets existed anywhere in the universe to having confirmed more than 5,500 of them. From not knowing whether the universe was expanding to knowing it is expanding and accelerating. From not knowing the structure of DNA to sequencing entire genomes in hours. From not knowing whether gravitational waves existed to detecting them with instruments sensitive enough to measure a disturbance 1,000th the diameter of a proton. The pace is not slowing. The James Webb Space Telescope is reading the atmospheres of distant worlds right now as you watch this video. The extremely large telescope, currently under construction in the Atacama Desert in Chile, with a primary mirror 39 meters across, will, when it begins operating in the late 2020s, be capable of directly imaging Earth-sized planets in the habitable zones of nearby stars. Not just detecting their atmospheric signatures, actually imaging them, resolving them as more than a point of light. We are in the early sentences of a story whose later chapters we cannot yet read. And the fact that the distances are vast, that the physics of crossing them is brutal, that the best shortcut we have imagined introduces problems as deep as the ones it was meant to solve, none of that tells us where those later chapters end. It tells us where we are right now, not where we will be. Here is the tension I want you to hold as we go into the next part. Something that rarely gets discussed in this context, and that is the question of timescale. Not how long it takes to cross the distance. We have talked about that extensively. But how long it takes for a civilization, a species, to go from where we are now to wherever the solution to the distance problem actually lives. Because here is a question that should genuinely recalibrate how you think about all of this. We are roughly 400 years into modern science. 400 years from Galileo pointing a telescope at Jupiter's moons to the James Webb Space Telescope reading the chemistry of worlds 100 light-years away. 400 years of compounding knowledge, compounding technology, compounding capability. What does 4,000 years of that look like? What does 40,000? What does 400,000? A span equal to the entire history of our species as Homo sapiens, of compounding scientific and technological development look like? We genuinely do not know, and that uncertainty cuts in both directions. Maybe the distance problem has a solution we cannot currently imagine, waiting to be discovered in some future physics that rewrites what we thought we knew. Maybe it does not. Maybe the constraints are as deep as they look from here. But the honest answer, the epistemically humble, scientifically grounded, cosmically aware answer, is that we do not know. We are at the beginning. And what comes now is the part of this conversation that I think should leave you not with despair at the distances, but with something that feels much more like wonder. If you are still watching, make sure to give this video a like and subscribe to the channel. You'll be part of a community that explores the cosmos together. There is a map that exists right now, sitting in the data archives of the European Space Agency, that contains the precise positions and motions of roughly 1.8 billion stars in the Milky Way galaxy. 1.8 billion. Not estimated, not modeled, measured, individual stars, each one with a catalogued position accurate to within micro-arcseconds. A unit of angular measurement so small that 1 micro-arcsecond is roughly the angular size of a human hair seen from the distance of the Moon. This map was produced by the Gaia Space Observatory, launched in December 2013, which spent years scanning the entire sky with a precision that would have been considered fantastical by any astronomer working even 2 generations ago. Gaia did not just measure positions. It measured proper motions, the actual movement of each star across the sky over time. It measured radial velocities, the speed at which stars are approaching or receding from us along our line of sight. It measured stellar brightnesses, colors, and in many cases compositions. What Gaia built is not just a snapshot, it is a dynamic model of a significant portion of our galaxy, a map of where the stars are and where they are going. A tool that allows astronomers to rewind the history of the Milky Way, to trace stellar orbits backward in time and understand how the galaxy assembled itself, and to project forward to understand how it will evolve. I want you to sit with what that means for a moment. 1.5 billion years ago, the stars that now sit in one region of the galaxy were somewhere different. Their orbits have carried them to where they are now, and Gaia's data is precise enough to reconstruct that journey. We are not just mapping the galaxy, we are reading its autobiography. And hidden within that autobiography are facts about the stellar neighborhood that change the interstellar distance conversation in ways that are not always appreciated. The stars are not stationary. This sounds obvious when stated plainly, but its implications are profound and underappreciated. Every star in the Milky Way is in motion. Our Sun orbits the galactic center at roughly 230 kilometers per second, completing one full orbit approximately every 225 million years, a span of time sometimes called a cosmic year or a galactic year. The last time our Sun was in the same position in the galaxy relative to the galactic center, the dominant land animals on Earth were early dinosaurs. Before that, one galactic year earlier still, there were no land vertebrates at all. But while stars share a broad orbital motion around the galactic center, they also have individual peculiar velocities, slight deviations from the average orbital motion unique to each star. These peculiar velocities mean that the distances between stars are not fixed. Stars drift relative to one another over time, and over sufficiently long timescales, the stellar neighborhood changes. There are stars that are currently far from us that will, in tens of thousands of years, pass through our cosmic neighborhood, and there are stars that are currently nearby that will equally drift away. The nearest stars to us today are not the nearest stars that have ever existed in our neighborhood, and they are not the ones that will be nearest in the future. Gaia data has allowed astronomers to identify several such close encounters. A star called Gliese 710, a dim orange dwarf currently sitting roughly 63 light-years away, is heading toward us at roughly 14 kilometers per second. In approximately 1.3 million years, it will pass within roughly 13,000 astronomical units of our Sun. That is still an enormous distance by everyday standards, roughly 200 billion kilometers, but in stellar terms it is extraordinarily close. Close enough that its gravitational influence could significantly perturb the Oort cloud, the vast reservoir of comets at the outer edge of our solar system. This is not directly relevant to interstellar travel as a near-term concept. 1.3 million years is not a planning horizon any current civilization is working on. But it illustrates something important about the nature of the distance problem across genuinely long timescales. The universe is dynamic. The stellar neighborhood is not a fixed geography. Given enough time, the kind of time that a truly long-lived civilization or a patient, distributed intelligence might operate on, the distances between specific stars change. The problem of crossing 40 trillion kilometers to the nearest star is a problem defined by where that star is right now. On longer timescales, the map rewrites itself. Now, I want to introduce a concept that I think is one of the most mind-expanding ideas in serious long-term thinking about civilization and the cosmos, and that almost never comes up in popular discussions of interstellar travel. It is called the Dyson sphere, named after Freeman Dyson, the same physicist who worked on Project Orion, a man whose imagination operated consistently at a scale that made other visionaries seem cautious by comparison. Dyson published a short but extraordinarily influential paper in 1960 titled Search for Artificial Stellar Sources of Infrared Radiation in the journal Science. In it, he proposed that a sufficiently advanced civilization would eventually face a fundamental energy constraint. The energy output of its home planet would become insufficient for its needs, and would therefore be motivated to capture a larger fraction of the energy output of its host star. The logical endpoint of that process, Dyson argued, is a structure, not necessarily a solid shell, but a swarm of habitats, solar collectors, and infrastructure surrounding the star and capturing most or all of its energy output. A Dyson sphere, in the most complete version of the concept, is a civilization that has essentially colonized its entire solar system and harnessed its star. The energy available to such a civilization is staggering. Our Sun outputs approximately 3.8 times 10 to the 26th power watts. A civilization capturing even a modest fraction of that, say 1%, would have access to roughly 3.8 times 10 to the 24th power watts. That is roughly 10 to the 11th power times the total current energy output of human civilization, 100 billion times what we currently use. At that energy scale, the conversation about interstellar travel changes completely. The warp drive energy problem, which at our current civilizational level involves energy scales that dwarf our entire planetary output, becomes a different kind of question for a Dyson sphere civilization. Not easy, but perhaps not impossible. And Dyson's insight was not just theoretical speculation. It was a practical proposal for how to search for advanced civilizations. A Dyson sphere, or even a partial Dyson swarm, intercepting a fraction of a star's light, would re-radiate the absorbed energy as waste heat in the infrared. It would look, to a telescope, like a star that emits anomalously in the infrared relative to its visible light output. That is a detectable signature, a real physical, observable consequence of the existence of advanced civilizations. Astronomers have searched for Dyson sphere candidates in infrared survey data. The most famous candidate, the star known as KIC 8462852, nicknamed Tabby's star after the astronomer Tabetha Boyajian, who led the team that first characterized its bizarre behavior, showed unusual, irregular dimming patterns that briefly attracted enormous attention as a possible megastructure candidate. Subsequent analysis found more mundane explanations: a cloud of dust, possibly from a disrupted comet or exocomet activity, but the episode illustrated that the search is real, the methodology is sound, and the universe does occasionally show us things that make us look twice. No confirmed Dyson sphere has been found, but the search continues, and it is a genuine scientific program, not a fringe enterprise. The absence of obvious Dyson spheres in our galactic neighborhood is itself data, more data feeding the great silence of the Fermi paradox. Let me now take you somewhere that I think fundamentally recontextualizes the entire arc of this video, and it requires us to think not just about space but about time in a way that human intuition genuinely struggles with. The universe is 13.8 billion years old. Our sun is 4.6 billion years old, which means it formed when the universe was already more than 9 billion years old. It is a relatively young star in the context of the universe's total history, the second or third generation of stars forged from material that had already been through at least one cycle of stellar birth, nuclear burning, and explosive death. There are stars in the Milky Way that are far older than our sun, stars that formed in the universe's first few billion years and have been burning ever since. Small, dim, red dwarf stars, M-type stars, burn their hydrogen so slowly and so efficiently that they can live for tens or even hundreds of billions of years. The smallest red dwarfs have calculated lifespans of roughly 10 trillion years, nearly 1,000 times the current age of the universe. Every red dwarf that has ever formed is, in a sense, still in the early chapters of its life. Red dwarf stars also happen to be the most common type of star in the galaxy. They make up roughly 70 to 80% of all stars, and many of them are known to host planets. Now, here is the thought that I want you to hold carefully, because it is genuinely vertiginous. If life can arise around red dwarf stars, And there are significant debates in astrobiology about the habitability challenges of red dwarf planets, including issues of tidal locking, stellar flares, and reduced photosynthetically useful radiation. But if it can, then there are potentially worlds out there where life began not 4 billion years ago as it did on Earth, but 8, 10, or 12 billion years ago. Worlds where whatever evolutionary process operates has had 3 times as long as it had here to produce complexity, consciousness, intelligence, and civilization. A civilization that has existed for even 1 million years longer than ours would be, by any reasonable extrapolation, so far beyond our current level of scientific and technological development as to be effectively incomprehensible to us. We have gone from horse-drawn transport to interplanetary probes in less than 200 years. Extrapolate that rate of development with all its uncertainties and non-linearities for 1 million years, and you get something that makes current human civilization look like a campfire next to a star. A civilization 10 million years old, 100 million, 1 billion. We have no framework for imagining what those look like. Our science fiction gives us humanoid aliens with slightly different foreheads. Our intuition gives us beings that feel broadly like us with better technology. But the honest answer is that a genuinely ancient civilization, one that has been building, learning, and evolving for hundreds of millions of years, would likely operate on principles and with capabilities so far beyond our current comprehension that we might not recognize it as a civilization at all. This is one of the more sobering proposed solutions to the Fermi paradox, not that advanced civilizations do not exist, but that they have become so different from what we imagine that our search strategies are simply misaligned with what we should be looking for. We search for radio signals because radio is what we use. We search for Dyson spheres because energy harvesting is something we can imagine a more advanced version of ourselves doing. We look for things that look like us, only bigger and more powerful. But a civilization 1 billion years older than ours might have left behind not radio waves and megastructures, but something we do not have a name for yet. Something that operates at scales or in regimes of physics that we have not yet discovered. Something that looks, to our current instruments, like background noise or natural phenomena or simply nothing at all. The physicist and author Arthur C. Clarke articulated this as his third law, that any sufficiently advanced technology is indistinguishable from magic. But I think the more precise version, and the more unsettling one, is this. Any sufficiently advanced civilization may be indistinguishable from nature, not because it is hiding, but because what it does and how it does it is so far beyond our current concepts that we literally do not have the cognitive or instrumental framework to tell the difference. If that is even partially true, the silence of the cosmos takes on a different texture, not an empty silence, a silence full of things we cannot yet hear. Now, there is a practical dimension to all of this that brings us back, sharply, to the distance problem. Even if we accept that the universe may be far more populated than our current observations suggest, even if we accept that ancient, incomprehensible civilizations may exist somewhere in the galaxy, the distances still enforce a particular kind of isolation on any species at our level of development. We cannot reach them. We cannot communicate with them in any meaningful conversational sense. We are separated by the same void that separates us from the stars themselves. And here is the particular cruelty of that situation. If you let yourself feel it fully, the knowledge that could potentially tell us how to cross the void. If any sufficiently advanced civilization has figured it out, is sitting in the heads, or whatever passes for heads, of beings we cannot reach, in systems we cannot visit, across distances that defeat our best current physics. If anyone in the galaxy has solved the warp drive problem, we cannot ask them how. If anyone has found a way to make the distances navigable, Their answer travels toward us at the speed of light, arriving perhaps thousands of years after it was sent, from a civilization that may have transformed beyond recognition in the interval. The very isolation that makes the distance problem urgent also makes the most likely source of its solution unreachable. That is a genuinely strange and uncomfortable loop. And sitting with it honestly, without either dismissing it as too speculative or catastrophizing it into hopelessness, requires a particular quality of mind. A quality that I think is one of the most distinctly human things there is, the ability to hold an unsolvable problem, to keep looking at it, to refuse to look away and refuse to give up, and to find in that refusal something that feels not like futility but like purpose. Let me tell you something about the overview effect. It is a term coined by the writer Frank White in his 1987 book of the same name, describing a cognitive shift reported by a significant number of astronauts after seeing the Earth from space. Not all of them, but enough to constitute a pattern worth taking seriously. The experience, described independently by astronauts from different countries, different cultural backgrounds, different political perspectives, goes something like this. You see the Earth from outside it, not in a photograph. You have seen photographs, but in person, through a window, with your own eyes. And something shifts. The boundaries, national borders, the divisions that structure daily human life on the surface are invisible. The atmosphere, the thin blue line that separates everything alive from the vacuum of space, looks impossibly fragile. The planet looks small, not diminished, small in the way a precious thing is small, cradled in darkness, self-luminous with reflected sunlight, surrounded by a void so absolute that the contrast makes it glow. Astronauts who have experienced this. Edgar Mitchell, one of only 12 humans to walk on the moon, described it as a sudden, overwhelming sense of connectedness. Ron Garan, who spent time on the International Space Station, called it a tragic realization. The recognition of the beauty and the fragility simultaneously. Chris Hadfield, the Canadian astronaut and commander of the ISS, has described the Earth from orbit as the most beautiful thing he has ever seen, and the experience of seeing it that way as permanently changing how he understands his relationship to it. None of these people went to space and came back thinking the distances were irrelevant. None of them stopped caring about Earth or the people on it. What changed was the frame, the context in which Earth and the distances and the void all sit together. I raise the overview effect here because I think it points towards something important about how the distance problem should ultimately be understood. Not purely as a physics challenge, not purely as an engineering challenge, but as a perspective challenge, a challenge of scale and frame and context that, when engaged with honestly and fully, changes not just what we see but how we see ourselves. Here is where I want to land as we approach the final stretch of this conversation, parts 9 and 10. We started this video with a question that sounded like it was about propulsion. Why won't warp drive save us from the distance between stars? And on the surface, the answers are physical, exotic matter, energy requirements, radiation, quantum instability, causal isolation, the Tsiolkovsky rocket equation, the hostility of the interstellar medium, the timescales of civilization. But underneath those physical answers, the real question has been something different. Something that the physics keeps pointing toward without quite saying directly. The real question is what the distances mean, not just as obstacles to travel, but as features of the universe we inhabit. Not just as engineering problems, but as facts about the cosmic context in which we find ourselves. Facts that, when understood clearly and fully, tell us something about who we are, what we are part of, and what it means to be a conscious, curious species in a universe whose scale dwarfs everything we have ever built. The distances are not just barriers. They are the architecture of isolation that makes each star system, each world, genuinely individual, genuinely unique, separated from every other by a void so vast that what happens on each world happens in a profound sense independently, without reference to what is happening anywhere else. That isolation is part of what makes us what we are. The fact that Earth's story unfolded without interference from any other intelligence, that whatever we have become, we became here, on our own, working with the resources and the physics and the biology of this one small world, is inseparable from the story itself. The distances did not just make the journey hard, they made the destination meaningful. This is where we ask what comes next, not in the distant, hypothetical future of warp drives and Dyson spheres, but now, in the decades immediately ahead, in the missions already funded, the telescopes already being built, the generation of scientists already working on the specific questions that will define humanity's next chapter in its relationship with the stars. I think you are going to find it more immediate and more extraordinary than you expect in the Atacama Desert of northern Chile, at an altitude of roughly 3,060 meters above sea level, on a plateau called Cerro Armazones. Construction crews are building something that has no precedent in the history of human engineering. Not in the history of astronomy. In the history of engineering, full stop. The extremely large telescope, its name is not poetic, it is literal. When it sees first light, currently projected for the late 2020s, it will have a primary mirror 39 meters across, roughly the length of 4 double-decker buses placed end to end. It will be composed of 798 individual hexagonal mirror segments, each one polished to a surface precision measured in nanometers. Its light collecting area will be roughly 13 times greater than any single optical telescope currently in operation. And what it will be able to do, what it is specifically designed to do, goes well beyond anything previous telescopes have managed. It will directly image planets in the habitable zones of nearby stars, not detect their gravitational influence on their host star, not observe their atmospheric signatures during a transit, actually resolve them as individual objects separated from the glare of their stars, captured in direct light. For the first time in human history, we will be able to look at another potentially Earth-like world and see it, not as a data point, not as a spectroscopic signature, as a visible object in our sky with its own reflected light, its own color, its own character. The philosophical weight of that moment, the first direct image of a world that might host life, is something I do not think our culture has fully prepared for. We have been discussing the possibility of life elsewhere for centuries. We have been scientifically searching for it for decades, but we have never seen it, not even the candidate worlds. We have seen data about them, models of them, artistic representations of them. The extremely large telescope will give us something qualitatively different. It will give us the thing itself. Let me tell you about some of the other missions already in progress or in advanced development that are quietly building the foundation of humanity's next chapter in its relationship with the stars. The Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, who played a pivotal role in making the Hubble Space Telescope a reality, is currently scheduled for launch in the mid-2020s. It has a wide field of view, roughly 100 times greater than the Hubble Space Telescope's infrared camera, meaning it can survey enormous swaths of sky in a single observation. One of its primary scientific goals is exoplanet detection and characterization. It is expected to discover thousands of new exoplanets, including many that transit their host stars at geometries that make atmospheric characterization possible with the James Webb Space Telescope or its successors. The European Space Agency's Plato mission planetary transits and oscillations of stars, is designed to find and characterize Earth-like planets orbiting Sun-like stars in or near their habitable zones, with a specific focus on measuring planetary radii and stellar ages, precisely enough to determine whether the conditions for complex life might exist. It is built to find the worlds that are not just interesting in principle, but specifically interesting as potential analogues to Earth, rocky, temperate, orbiting a stable star with a known age. And then there is the concept that has been developing within the NASA astrophysics community for years, sometimes called the Habitable Worlds Observatory. This proposed next-generation space telescope is designed from the ground up to directly image Earth-sized planets in the habitable zones of Sun-like stars within roughly 20 light-years of Earth, and to perform detailed spectroscopic analysis of their atmospheres, searching specifically for the combination of gases that, in our current understanding of biochemistry, would constitute compelling evidence of life. Oxygen, ozone, methane, water vapor, in particular ratios and concentrations that abiotic chemistry would struggle to explain. This telescope does not exist yet. It is a scientific priority. Endorsed by the Astro 2032 Decadal Survey, the document produced every 10 years by the United States National Academies of Sciences that sets the direction for American astronomy and astrophysics for the coming decade. It represents the considered judgment of the astronomical community about what the most important scientific questions are and how to answer them. And the question it is designed to answer is the one: are we alone? I want to be specific about the timescale here, because I think it matters enormously for how you understand the moment we are in. The James Webb Space Telescope launched in 2021. The extremely large telescope will see first light sometime in the late 2020s. The Roman Space Telescope launches in the mid-2020s. Plato follows in the early 2030s. The Habitable Worlds Observatory, if it follows the development timeline of previous flagship space telescopes, might fly sometime in the 2040s. You are, in all likelihood, going to be alive when the first compelling spectroscopic evidence of life beyond Earth is announced, or when the first direct image of a habitable zone Earth analog is captured, or when the first signal from another intelligence, however ambiguous, however contested, however uncertain, arrives in our instruments and refuses to be explained away. I do not say this as empty optimism. I say it because the tools are being built right now, the missions are being funded right now, the observations are being made right now. The trajectory is real. The only question is exactly when along that trajectory the threshold gets crossed, and whether the answer, when it comes, is the presence of life or its confirmed absence, both of which would be, in different ways, transformative. Think about what it would mean if the James Webb Space Telescope, or its successor, detected a clear, unambiguous biosignature on a world 100 light-years away. A combination of gases that no known abiotic process can produce. A world where the chemistry, read through hundreds of light-years of space by a mirror and a spectrograph, is doing something that unambiguously requires life. We would know. Not where that life is exactly. We know the star, we know the planet's orbital parameters, we know its atmospheric composition, but we do not know what its surface looks like or what its inhabitants, if any, look like. But we would know the thing that has haunted human imagination since we first looked up at the stars and wondered, we are not alone, and then the distance problem would transform. Overnight, not in its physics, the void between us and that world would be exactly as vast the morning after the announcement as it was the morning before, but in its meaning, in the urgency and the weight and the civilizational priority we assign to it. Because if we know something is there, the question of how to reach it, or at minimum how to communicate with it, however slowly, becomes not a speculative engineering exercise, but a species-defining imperative. Let us talk about communication specifically, because it is an aspect of the distance problem that tends to get overshadowed by the more dramatic question of physical travel, but which may in practice be the more immediate frontier. Radio communication with another civilization at even a modest interstellar distance involves time delays that redefine what communication means. At 100 light-years, a message takes 100 years to arrive, and any response takes another 100 years to return. A conversation, in any sense that resembles what we mean by that word, is impossible. What is possible is something more like correspondence, a very, very slow exchange of information across a very, very large distance. But slow does not mean worthless. The scientific, cultural, and philosophical content of a transmission from another civilization, even one that arrives with a lag of centuries, would be incomparably valuable. A mathematical proof, a description of physics we have not yet discovered, an account of a history unfolding on a different world, an artistic work created by a mind shaped by entirely different evolutionary pressures, expressing entirely different experiences of existence. The search for extraterrestrial intelligence, SETI, has been running in various forms since Frank Drake pointed a radio telescope at two nearby stars in 1960. The Allen Telescope Array in California, funded initially by a contribution from Microsoft co-founder Paul Allen, is one of the dedicated facilities for this search. Breakthrough Listen, a 10-year, $100 million initiative launched in 2015, with backing from the Russian-Israeli entrepreneur Yuri Milner, is currently the most comprehensive SETI program in history, scanning millions of stars across a wide range of radio and optical frequencies, with more telescope time than any previous SETI effort has ever had access to. These programs have not found anything, not yet, but they have systematically ruled out many hypothetical sources of artificial signals, and the negative results are themselves scientifically informative. They constrain what kinds of civilizations can exist, and where, and at what prevalence in our galactic neighborhood. And there is a parallel program, METI, or Messaging Extraterrestrial Intelligence, that raises an entirely different set of questions if we should be sending signals as well as receiving them. If the silence of the cosmos is partly because everyone is listening and no one is transmitting. If the appropriate next step for humanity is not just to continue searching passively, but to actively announce our existence to whatever might be listening. The METI debate is genuinely divisive within the scientific community. Stephen Hawking was among those who argued strongly against it, that deliberately attracting the attention of an unknown and potentially far more powerful civilization is an act of civilizational recklessness that we should not undertake without global consensus. Others argue that we have been leaking radio signals into space since the early 20th century anyway, that any civilization with sufficiently advanced instruments already knows we are here, and that deliberate, structured messaging would add little to the risk while potentially accelerating contact enormously. This is not a settled debate. It is an active one, with real stakes and no clear resolution, and it is happening now among scientists who are serious, informed, and deeply aware of the implications of either choice. Now let me bring you something that I think is one of the most quietly extraordinary developments in the entire landscape of near-future space science, and one that sits at an unusual intersection of the interstellar distance problem and the immediate practical capabilities of our civilization. In 2016, the Breakthrough Starshot initiative, the same breakthrough program behind Breakthrough Listen, announced an ambitious plan to develop a fleet of gram-scale spacecraft, each equipped with a light sail and a miniaturized array of sensors, to be accelerated by a ground-based laser array to roughly 20% of the speed of light. At that velocity, such a craft could reach the nearest star system in approximately 20 years. We discussed the Starshot concept briefly in Part 4. But what I want to return to here is something slightly different, what Starshot represents as a statement about where humanity actually is in its relationship with the interstellar distance problem. The Breakthrough Starshot initiative is not a government program. It is not a NASA mission or an ESA project. It is a privately funded research and development effort, backed by a commitment of $100 million for the initial research phase, announced at a press conference featuring Stephen Hawking and Yuri Milner and the physicist Freeman Dyson, the same man who imagined Dyson spheres and designed nuclear pulse propulsion for Project Orion. The fact that a private initiative can now seriously, credibly, scientifically engage with the question of interstellar travel, not in the sense of building a warp drive, but in the sense of actually sending something to another star system within a human lifetime, tells you something important about where we are on the developmental curve. The challenges are enormous. The laser array required to accelerate the Starshot craft to 20% of the speed of light would need to produce roughly 100 gigawatts of power during the acceleration phase, comparable to the entire electrical generating capacity of several large countries. The light sails must be extraordinarily thin and reflective, surviving the intense radiation environment during acceleration. The communication link back to Earth from a craft moving at a fifth of the speed of light is a genuinely difficult engineering problem, and perhaps most sobering, the craft cannot slow down. At 20% of the speed of light, with no onboard propulsion, the fly-through of the destination star system would last a matter of hours before the craft was gone into the void on the other side. But these are engineering challenges. They are hard, they may require decades to solve, but they are not forbidden by any known law of physics. And that distinction between hard and impossible is one that keeps mattering over and over in every chapter of this story. There is a concept in the study of complex systems called an inflection point, the moment on a growth curve where the rate of change itself begins to accelerate, where what was gradual becomes rapid, where the accumulation of incremental progress crosses some threshold and produces qualitative change rather than merely quantitative improvement. I think we are approaching an inflection point in humanity's relationship with the cosmos, not the moment of interstellar travel that remains distant in every scenario currently on our drawing boards, but the moment at which the questions we are asking about the universe become answerable in ways they never previously were. For most of human history, the question of whether life exists elsewhere in the universe was philosophical. It was a question for theologians and philosophers and poets, not scientists. There was no data. There was no instrument sensitive enough to gather data. There was no methodology for converting the question from speculation into measurement. That changed within the last generation. In less than 30 years, we have gone from knowing of no planets beyond our solar system to knowing of more than 5,500. We have gone from theorizing about exoplanet atmospheres to measuring them directly. We have gone from the Fermi paradox being a dinner table puzzle to it being a subject of rigorous scientific research programs funded at the scale of hundreds of millions of dollars. The inflection point is not behind us, but we can see it ahead. And what is remarkable, what I find genuinely moving about this particular moment in history, is that the generation alive right now is the generation that will cross it, not the generation that builds the warp drive, not the generation that lands on a world orbiting another star, but the generation that first knows, with scientific rigor, with observational evidence, with reproducible data, whether life is a singular accident or a cosmic constant, that is not a small thing. That is arguably the most significant piece of information our species has ever stood on the threshold of obtaining. And so I want to ask you something directly as we come to the final part of this video. What do you do with that? When you hold all of this together, the distances that defeat our best physics, the warp drives that introduce problems as deep as the ones they solve, the generation ships that ask more of humanity than humanity can currently give, the telescopes that are reading the chemistry of distant worlds in real time, the missions that will answer the great question within the span of a human lifetime, what is the appropriate response? Is it despair at the distances? I do not think so. The distances are real, but they are also, in a sense, the price of living in a universe large enough and old enough and complex enough to produce us. A smaller universe, a universe in which the stars were close enough to visit casually, would be a different kind of universe. One that probably could not have produced the conditions for life in the first place. Is it resigned acceptance? I do not think that either. The history of this conversation, the history of human engagement with the cosmos, is a history of refusing resignation, of looking at the distance from here to the moon and building something that crossed it, of looking at the distance from here to Mars and pointing a rover at its surface, of looking at the complexity of a living cell and developing tools fine enough to read its genome. Resignation is not in the vocabulary of the enterprise that produced all of that. What I think the appropriate response is something that sits between despair and naive optimism, a clear-eyed, evidence-based, cosmically aware recognition that we are not at the end of the story. We are not even close to the end. We are, by almost any meaningful measure, at the very beginning. And beginnings, however hard they are also the most interesting place to be. There is a photograph taken on the 14th of February 1990 that I want you to picture in your mind. You have probably seen it. Most people have. But I want you to look at it again, here, at the end of this conversation, because I think it means something different now than it did before we started. The Voyager 1 spacecraft, launched in September 1977, carrying a golden record encoded with sounds and images of Earth, a message in a bottle thrown into the deepest ocean imaginable, had by 1990 traveled beyond the orbit of Neptune, roughly 6 billion kilometers from the Sun. At the request of Carl Sagan, NASA commanded it to turn its camera back toward the inner solar system and take one final photograph before the camera was switched off permanently to conserve power for the long journey ahead. The image it returned shows a vast dark emptiness scattered with streaks of light, artifacts of the camera's optics, sunlight scattering across the lens, and in one of those streaks, barely visible, a pale blue dot, less than a pixel in size, a mote of dust suspended in a sunbeam, Earth, our entire world. Every human being who had ever lived, every civilization ever built, every war ever fought, every love ever felt, every work of art ever created, all of it contained in a point of light so small it barely registers against the darkness surrounding it. Sagan wrote about that image in words that have become among the most quoted in the history of science communication. He wrote that the pale blue dot underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. I want to add something to that. Standing here at the end of everything we have been through in this video, the pale blue dot is also the only place in all the cosmos we have so far explored where we know for certain that the universe is aware of itself, where matter has organized itself into something that can look outward and ask questions about what it sees, where chemistry has become curiosity, where physics has become wonder. That is not nothing. That is, by any measure, extraordinary. Let us do a final accounting of what we have learned. We started with the distance. not as an abstraction but as a physical reality, 41 trillion kilometers to the nearest star system, a gap so vast that even traveling at the fastest speeds any human-made object has ever achieved, the journey would take tens of thousands of years. We established that this distance is not simply large in the way that the distance across a continent is large. It is large in a way that defeats intuition entirely, a way that requires us to abandon our everyday sense of scale and replace it with something that feels almost more like philosophy than geography. Then we turned to the proposed solution, the Alcubierre warp drive, a genuine mathematical framework derived from Einstein's field equations of general relativity that in principle allows a spacecraft to travel between points in space faster than light without the spacecraft itself ever exceeding the local speed of light. We established that this is not science fiction in the sense of being physically forbidden. It is science fiction in the sense of being practically unobtainable with anything resembling our current understanding of physics and engineering, the exotic matter problem, the energy requirements that dwarf the output of stars, the radiation that builds up at the leading edge of the warp bubble and would sterilize the destination upon arrival, the causal isolation that makes steering impossible once the bubble is activated, the quantum instability at the Cauchy horizon. Each of these is not a detail to be engineered around. Each is a fundamental consequence of the physics that makes the warp drive concept work in the first place. We explored the alternatives. Breakthrough Starshot, real, funded, scientifically credible, capable of reaching a nearby star in roughly 20 years, but carrying no human, unable to slow down, and dependent on engineering achievements that remain decades away. Generation ships, capable of carrying human biology across the void, but requiring a social, psychological, and biological resilience that we have never demonstrated and may not be capable of demonstrating. Nuclear pulse propulsion, theoretically more powerful than anything else we have seriously considered, but politically constrained and still orders of magnitude too slow for any destination beyond the nearest stars. We asked whether the traveler of the future might need to be something other than biological, a digital consciousness, an artificial intelligence, a post-human entity capable of surviving timescales and radiation environments that would destroy organic life. We found that this possibility is real, but opens philosophical questions about identity, continuity, and what we mean by humanity that we have barely begun to address. We looked at what the universe itself has to say about the distance problem through the James Webb Space Telescope, reading the atmospheres of distant worlds, through the Gaia Observatory mapping the dynamic, living geography of our galaxy, through the search for biosignatures and the deepening mystery of the Fermi paradox. We found a cosmos that is simultaneously more knowable than we imagined and more isolating than we hoped. A universe in which the tools to understand the distances are advancing rapidly while the tools to cross them remain stubbornly primitive, and we arrived, finally, at the recognition that the distance problem is not purely a physics problem. It is a perspective problem, a civilizational problem, a problem that asks us not just what we can build but who we are, what kind of species we want to be, on what timescale we are willing to think, and whether our relationship with the cosmos can mature beyond the desire to conquer it towards something more like the willingness to know it. Here is what I believe, standing at the end of all of this, and I want to be clear that this is not a scientific claim. It is a considered perspective based on the science, but reaching beyond it into something that the science alone cannot resolve. I believe the distances are real, and I believe they matter. I believe that warp drive, in the Alcubierre formulation, faces obstacles that are not merely engineering challenges, but consequences of the same physics that makes the universe comprehensible, and that solving them, if it is possible at all, will require a revolution in our understanding of physics comparable to the one that produced quantum mechanics and general relativity simultaneously and probably larger. I believe that the alternatives, generation ships, light sail probes, nuclear propulsion, are genuine and worth pursuing, but that none of them on the timescales relevant to our civilization as it currently exists closes the gap in a way that makes the stars accessible in the way that, say, Antarctica became accessible. They make the nearest stars reachable, perhaps. They do not make the galaxy navigable, and I believe that none of this is a reason for despair. Not because the problems are smaller than they look. They are not. They are exactly as large as they look, and in some cases larger. But because the appropriate response to a genuine, deep, hard problem is not despair. It is engagement, curiosity, the sustained intergenerational, compounding effort that our species has demonstrated, imperfectly, inconsistently, but unmistakably, that it is capable of. Think about the arc of the last century alone. In 1920, the idea that humans would walk on the moon within 50 years was not science fiction. It was not even science fiction. It was not seriously imagined. The Wright brothers had achieved the first powered flight less than 2 decades earlier. Rockets capable of reaching orbit were not yet a concept in the minds of the people who would build them. The physics of spaceflight, the Tsiolkovsky rocket equation, the orbital mechanics, the understanding of the space environment were known, but the idea that they would be practically implemented within a human lifetime was, at best, a dream held by a tiny number of visionaries who were mostly not taken seriously. Within 50 years, 12 human beings had walked on the surface of another world within 50 years. Of what, in 1920, was not even seriously imagined. I am not saying the stars will be reached within 50 years. They will not. The distances are orders of magnitude greater than the distance to the moon. The physics challenges are categorically different. I am not making a naive optimism argument that the pace of progress will simply continue until everything is possible. I am making a different argument, a more careful one. I am saying that the history of human engagement with the impossible is a history of the impossible becoming repeatedly first imaginable, then feasible, then routine, and that the specific process by which that happens is not magic and not inevitability. It is the compounding of knowledge, generation by generation, each one building on what the previous one understood and discovered and built and failed at. The generation alive right now did not build the James Webb Space Telescope from scratch. They inherited the optics knowledge that came from Hubble. Hubble inherited the space telescope concept from the visionaries of the mid-20th century who first imagined placing a telescope above the atmosphere. They inherited the rocket technology that came from the space race. The space race inherited the theoretical physics that came from Einstein and the engineering that came from the Industrial Revolution and the mathematics that came from Newton and Leibniz and the astronomical tradition that came from Galileo and Kepler and Copernicus. Every discovery that the James Webb Space Telescope makes right now is the product of a chain of human effort going back centuries, and every discovery it makes becomes part of the chain that extends forward into the hands and minds of the people who will build what comes next, and the people who will build what comes after that, and the people, perhaps very different from us in ways we cannot fully imagine, who will eventually look back at our era the way we look back at Galileo, as the beginning of something, as the point at which a species first began to seriously reckon with the universe it inhabited. There is something I have not said explicitly yet in this video, and I want to say it now clearly because I think it is the most important thing. You are not a bystander to this story. I know that sounds like a motivational cliché. I know it is easy to hear and easy to dismiss, but I mean it in a specific non-cliched sense that I want to be precise about. The knowledge that makes this conversation possible, the understanding of general relativity and quantum mechanics and stellar physics and exoplanet science and astrobiology, is not the property of the scientists who produce it. It is the common inheritance of every human being alive. It belongs to you as much as it belongs to anyone in any observatory or any university physics department in the world. Not because you did the work to produce it, you did not, and neither did I, but because it is the product of a species-wide enterprise funded by societies, built on public education, communicated across generations through exactly the kind of medium you are engaging with right now, your curiosity about these questions, the fact that you are here, at the end of a video this long, about a topic this difficult, that offers no easy answers and no satisfying resolution. Your curiosity is not separate from the scientific enterprise. It is part of it. The questions that scientists choose to pursue are shaped, in part, by the questions that societies consider important. The funding that observatories receive, the political will that keeps space agencies operational, the cultural priority assigned to understanding our place in the cosmos, all of that is influenced by the aggregate curiosity of millions of people who are not scientists but who care about the answers. When you share a video like this, when you talk about the Fermi paradox with someone who has never heard of it, when you point out that the James Webb Space Telescope is reading the atmospheres of worlds 100 light-years away, and watch someone's face shift as they understand what that means. When you vote for representatives who take science seriously and fund research generously and think about the long term instead of just the next election cycle, you are part of the chain, not in the same way as the physicist who solves the exotic matter equation or the engineer who designs the next generation telescope, but part of it nonetheless. And chains are only as strong as every one of their links. The distances between the stars are real. They are not going away. The physics that makes them so hard to cross is not going to quietly relent because we want it to. The universe does not owe us proximity to our neighbors, and it has not provided it. But the universe did give us something else, something that might, in the very long run, matter more than the distances. It gave us the capacity to understand them. The ability to look at a gap of 41 trillion kilometers and measure it and name it and think about it and feel something about it. Awe, frustration, wonder, determination, and then go back to work on the problem anyway. No other animal on this planet does that. No other known entity in the universe does that. Whatever life might exist around other stars, whatever chemistry might be doing something we would recognize as living on a world the James Webb Space Telescope is currently studying, we do not know if any of it does what we do. Looks outward and asks not just what is out there, but how do I know, and what does it mean, and what do I do with that knowledge? We are, as far as we currently know, the universe's one confirmed experiment in that particular kind of consciousness. The one place where matter has organized itself into something that contemplates the distance between the stars and finds it, simultaneously humbling and beautiful and unbearable and inspiring. That is who we are. That is what we are doing here on this pale blue dot, in this thin atmosphere around this unremarkable star, on the outer edge of this spiral galaxy, in the middle of this cosmic moment that will not last forever, but that is, right now, ours. The stars are far away, farther than warp drives can easily reach, farther than generation ships can comfortably cross, farther than any technology currently on our drawing boards can make accessible on human timescales. And yet, the James Webb Space Telescope is reading their planet's atmospheres right now. The extremely large telescope is being assembled in the Chilean desert right now. Breakthrough Listen is scanning millions of stars right now. Plato is being built right now. The Habitable Worlds Observatory is being planned right now. a generation of scientists who grew up watching the Hubble Deep Field images and the first exoplanet discoveries and the detection of gravitational waves, is working on these problems right now. And you, watching this, thinking about this, feeling something about this, you are part of right now too. The distance between the stars is not the end of the story. It is the condition under which the story is being written, and we are nowhere near the last page. Look up tonight if you can. Find a dark patch of sky away from the city lights, if you are able, and look at the stars, not as lights in a dark field, but as what they actually are. Other suns, distant, ancient, burning with nuclear fire in the void, each one potentially surrounded by worlds, each world potentially hosting something that, in whatever form it takes, is doing what we are doing right now, looking out, wondering, reaching toward an understanding that the distances make hard but do not make impossible. We are made of star stuff, as Carl Sagan said. The calcium in our bones and the iron in our blood were forged in the interiors of stars that died before the sun was born. The universe built us out of itself, and then gave us the capacity to look back at it and ask why. The stars are far away, but they are not strangers. They are in the deepest physical sense possible, where we came from. And maybe, across timescales longer than any individual life, through effort more sustained than any single civilization, using tools not yet imagined by minds not yet born, where we are going. Thank you for spending this time with me. If this video moved something in you, if it made the universe feel bigger and stranger and more worth understanding than it did before, then consider subscribing, because this is what we do here every week. We take the hardest, most beautiful questions in science and we sit with them honestly, without pretending the answers are simple, without pretending the mysteries are solved, because they are not, and that is exactly what makes them worth pursuing. I will see you in the next one. And if your brain is still spinning from all of this, if you want to feel the true scale of what we just talked about in your gut, click the video on your screen right now. We break down exactly how long it would actually take to travel just 1 light year, and the answer will genuinely shock you. Go watch it. You won't regret it.